Hello, welcome to the first introductory lecture of the free online course Science and Philosophy. My name is Dr. Orestes Palermos, and my colleague Dr. Adam Carter and I would like to guide you through some of the technical specifications and requirements of this course, and also talk you through the themes that it will cover. Science and Philosophy is the first in a series of three free online courses on the general theme of philosophy, science, and religion, and it focuses on a philosophical approach to the topic of science. The second course, Philosophy and Religion, is similarly focusing on a philosophical approach to religion. Finally, the third free online course, Religion and Science, builds on the philosophical approaches towards science and religion of the previous two courses in order to critically examine the debate between science and religion. Learners that follow all three courses will have gained an understanding of the main parameters in the current debate between science and religion. They will have gained familiarity with the relevant areas of science that feature in the debate, including disciplines such as cosmology, evolution, and the neurosciences. They will have encountered key philosophical approaches at the interface between science and religion, and they will have embarked constructively in some of the most interesting cross-disciplinary conversations. Most importantly, however, they will be more open to personal growth through commitment to dialogue across intellectual and spiritual boundaries. Some of the more specific topics that these three courses are going to cover will be topics like: is scientific knowledge the absolute truth? Is evolutionary biology scientific? And whether creationism is scientific? What makes us religious according to neuroscience? Could science and religion be compatible in the way they perceive the origin of the universe? What are the ethical dimensions of the science-religion debate? Each free online course consists of 4 to 5 modules, as well as satellite content. The modules and the satellite content contain lectures by leading experts across a variety of different disciplines, including philosophy, science, psychology, sociology, and the neurosciences. In order to pass each free online course, learners will have to successfully complete the multiple choice quizzes of each module. They're welcome to take the quizzes as many times as they wish, and they also have the option to answer comprehension essay questions that will be graded by other people taking the course like them. The satellite content of each course is also optional and won't contain any quizzes or essay questions, but learners are very welcome and strongly encouraged to follow this content as well, because it will provide them with a deeper understanding in the topics that each course is going to be dedicated to. Finally, in every module and satellite content, we have also included a list of related readings that learners will be able to freely access online. So these are some of the technical specifications and requirements of the first online course, which focuses on the nature of scientific knowledge, its limits, and the implications that these have for the debate at the intersection of philosophy, science, and religion.
Hello, my name is Alfred Mealy. I'm the William H. and Lucille T. Werkmeister Professor of Philosophy at Florida State University. I'm giving a talk in the Philosophy, Science, and Religion series. My talk is on free will and neuroscience. I'll mainly talk about science, especially neuroscience. I'll talk a bit about philosophy. And this topic has, of course, connections to religion, too, and philosophy of religion. I won't have much to say about religion in the talk, but I've been asked to say a few words about it at the beginning. And so there are certainly connections between free will and religion. For example, there's the problem of divine foreknowledge. So suppose God is omniscient, that is, God knows everything. Then it may seem to follow that God knows everything that everybody will ever do. and that God knows it in advance. But if God knows everything you're ever going to do, then it looks like you can't do otherwise than you actually do, in which case you might start worrying about free will. And free will comes in connection with religion in another way, too. Some people wonder why there's all the pain and suffering that exists in the world. They wonder why God would allow it. And one answer is that God allows it partly because it is produced by free actions of free human beings. But my main topic is going to be a collection of neuroscience experiments that have been claimed to show that free will is an illusion, that free will doesn't exist. And what I'll do is to explain why we can't get properly from the data that these experiments produce to the conclusion that there's no free will. And I won't do this in any fancy philosophical way. I'm mainly going to be paying attention to data and what the data show. So it's always useful, I think, for me anyway, to tell the audience a bit about my motivation for working on this topic. And what happened is I've always tracked science related to human action because my specialty really is human behavior. And years ago, the news started coming out that scientists had shown that there was no free will. And originally, I thought nobody was going to pay much attention to it because it's such a sort of shocking announcement. But then the news came out more frequently, and I started wondering what effect it would have on people. So would it depress people, or would they just not believe it, or would they find it a matter of relief that they don't have free will so they can't be blamed for bad things that they do? And eventually we started getting hard evidence about that, about the effect of the news on people's behavior, and I'll talk about that in a minute. I'll read you some quotations from the news just so you get a sense of it. So here's one. This is from April 2008, Science Now Daily News. Your mind might be made up before you know it. Researchers have found patterns of brain activity that predict people's decisions up to 10 seconds before they're aware they've made a choice. The result was hard for some to stomach because it suggested that the unconscious brain calls the shots, making free will an illusory afterthought. Or here's another one. It's from Science News, December 2008. The article was called The Decider. Some of you might remember that George Bush was the decider. Free will is not the defining feature of humanness, modern neuroscience implies, but is rather an illusion that endures only because biochemical complexity conceals the mechanisms of decision-making. And so that was 8 years ago, but the news is still coming out. Here's something from June 2016. There is no such thing as free will, based on a recent science experiment. Here's an example of something I got. This is an email out of the blue. I was, at the time, working on my book, Effective Intentions, which is a response to scientific arguments for the claim that there's no free will. And I received this from someone I don't know. Dear Dr. Mealy, I recently purchased a DVD by Dr. Stephen Walensky. He explains that from the point of view of neuroscience, there is no such thing as free will, as we can only perceive an action after it has already occurred. Can you please help me with this? I can understand that I don't know what thought will occur next, but that has already happened is beyond comprehension. Thank you, as I am in a lot of despair. And I thought, well, there's at least one person who was saddened or depressed by the news that there's no free will. Okay, and then as I mentioned, we started getting hard evidence about the effect of this news on people. The first study that was done on this was done by Kathleen Voss and Jonathan Schooler, a pair of social psychologists. And what they did was to divide their subject pool into 3 groups, and one group was given a passage to read saying that there's no free will, and another group was given pro-free will passages saying that you do have free will, And the third group was given neutral passages, passages having nothing to do with free will. And then the next task was to take a math quiz. And the subjects were told that the program was glitchy, so that if they didn't press the space bar right after the question showed up, then the answer would pop up on the screen, in which case, of course, they could cheat because they could see the answer. And what they discovered is that the group who read the no free will passages cheated way more often than the other two groups. And the other two groups behaved about the same, which is evidence that free will is a kind of default assumption. They did a version of this study in which, for correct answers, you got $1 for each one. And so by cheating, you were stealing. And the people who read the no free will passages then stole more often than the others. And then not long after, a friend of mine, a psychologist at Florida State University, Roy Baumeister, did a similar study. And what he did was to divide the subject pool into two groups. And one group read passages saying that there's no free will, and the other group read neutral passages. And then the next task was to serve snacks to people who were about to walk into the room. And the subjects were told two things about these people who were going to walk in. One, they've all indicated that they really hate spicy food. And two, they have to eat everything you put on their plate. And the group who read the no free will passages doled out way more of the spicy salsa option than the other group did. So here, again, lowering confidence apparently in free will increases misbehavior, and the misbehavior in this case is aggressive behavior, causing people pain and suffering by giving them food they don't like that they have to eat. So that was my motivation, really, for starting to write on this topic. And what I wanted to figure out was whether the studies, the scientific studies that are claimed to show that there's no free will, really do show that. If not, why not? And if so, why? Now, I'll start talking about the studies very shortly. I just need a little bit of terminology, and I'll introduce that, and then I'll get on to the first study. And as I mentioned, I'll talk about 3 different studies using 3 different kinds of technology. The terminology I need, deciding. So what is it to decide to do something? The way I think of it, and the way the scientists I'll be talking about tend to think about it, is as follows. To decide to do something is to perform a little mental action, a little momentary mental action of forming an intention to do it. So deciding is active, and it's active internally, and what it is to form an intention to do a thing. Intentions you can understand as you like. Turns out most people understand the word intention in basically the same way. And then among intentions and decisions, we have what I call proximal ones and distal ones. And a proximal intention is an intention you have now to do a thing now, like an intention I have now to raise my hand now. A distal intention or decision is an intention or decision now to do something later. For example, I intend now to have an extra cold Guinness with dinner tonight. All of the studies I'll be talking about are about proximal or nearly proximal intentions and decisions. Okay, so now on to the scientific studies. The first study I'll talk about is by Benjamin Libet. It was done in the early 1980s, and it is the neuroscience study that got the no free will ball rolling in neuroscience, a very influential study. Here are some quotations from the literature, some from Libet, most from Libet, and some from elsewhere. So the first one. The brain decides to initiate, or at least prepare to initiate, certain actions before there is any reportable subjective awareness that such a decision has taken place. So the brain decides things unconsciously, the person becomes aware of it later. Next quotation. Because brain activity in the supplementary motor area consistently preceded the conscious decision, it has been argued that the brain had already unconsciously made a decision to move even before the subject became aware of it. So that's basically the same point. It's from a paper published in 2008, and the technology used there was different from Libet's. It was fMRI, and I'll talk about that shortly. Now back to Libet. If the act now process is initiated unconsciously, then conscious free will is not doing it. And then another quotation from Libet, it's a generalization he makes. Our overall findings do suggest some fundamental characteristics of the simpler acts that may be applicable to all consciously intended acts and even to responsibility and free will. So what's being claimed here is that they have evidence that the brain unconsciously makes decisions that the person then becomes aware of later. And then there's a claim that if something is produced unconsciously, it's not produced freely, that is, free will is not involved in its production. And then we get the generalization claim that we can say, based on what goes on in these experiments, that all decisions are made unconsciously, in which case no decision is made freely, so we don't ever exercise free will in making decisions. And then the thought is, if a decision isn't freely made, any action that proceeds from that decision, that executes it, that flows from it, is not a free action. So you don't get any free actions at all. So this is how Libet's study went, the main study he did. So subjects are seated in chairs, and their task is to flex a wrist whenever they want. They're watching a very fast clock. It makes a complete revolution in 2.5 seconds. What they're supposed to do is flex whenever they want, and then after they flex, they're supposed to report where the hand was on the clock when they first became aware of their urge or wish or will or intention or decision. Different terms were used to flex right now. They're hooked up to 2 machines, so EEG readings are taken from the scalp. These are readings of electrical conductivity on the scalp. And readings are taken from the wrist muscle. So what you can do then is see when the EEG ramp-up started and then do some comparisons. And what they discovered when subjects were regularly reminded to be spontaneous, that is, not to plan in advance or think in advance about when to flex, is that you got an EEG ramp-up about 550 milliseconds, that is a little more than half a second, before muscle motion started. So muscle motion starts at 0, the ramp-up starts a little over half a second before 0, and the average time of first reported awareness of the urge or decision or intention was about 200 milliseconds before muscle motion. And so the conclusion that was drawn is that the brain is making the decision to flex the wrist now, a little more than half a second before the muscle starts moving, the wrist muscle, and the person doesn't become aware of that intention or decision for another third of a second after it's made. And so the claim is the decision isn't made freely, and then, of course, they generalize. Now, I should make a couple of points before moving on to the next experiment. So, Libet, unlike almost all of his followers, thought that once you became aware of your intention or decision or urge to flex now, you had time to veto it. So you had a kind of veto power. And the window of opportunity for an exercise of veto power is about 1/10 of a second, he thought. And after that time, you're going to hit the point of no return, so it's going to be too late to cancel the urge, and muscle motion will be generated. Libet thought he had 2 different kinds of evidence for veto power. So one kind was that after the experiment, many of the subjects said to him, you know, sometimes I had an urge to flex right away, but I didn't do it. I just waited for the next one to come along and I acted on that, or I waited for 2 more to come along and I acted on those. So that's kind of anecdotal evidence of veto power. But Libet also did a veto study. And in the veto study, the subjects were told to prepare to flex when the spot hit a certain point on the clock. Libet actually used a spot. These days we use hands. But so prepare to flex when the spot hits a certain point on the clock, but don't do it. So just to select a point, let's say the 9 o'clock point on the clock. So prepare to flex when the spot hits there, but don't do it. And what Libet discovered is that subjects in that condition displayed a different EEG. So we could imagine it like this. Their instruction is to prepare to flex when the spot hits the 9 o'clock point, but don't do it. And what Libet discovered is that when subjects were given that instruction, you got an EEG ramp up that started earlier, started about a second before the designated time, like the 9 o'clock time on the clock, and then petered out 150 to 250 milliseconds before the designated time. And Libet said, look, I found it. Now we have evidence of veto power. Okay, so now I have described to you Libet's veto experiment, and there is a problem with it that I would like to describe to you now, and then I'll get on to the next 2 science studies, and then I'll move on to the critique. So what Libet thought he showed with this veto study is that people actually had the power to veto intentions to do a thing at a certain time. So his thought was, well, these subjects, given the instructions I described to you, intended to flex when the spot or hand hit the 9 o'clock point, and then vetoed that intention and did not flex. But there's a problem with Libet's reasoning here, and I could give you a complicated explanation of the problem, or we could do our own hands-on experiment, you and I together. So let's do the hands-on thing. It's way simpler. So what I want you to do is to prepare to snap your fingers like this when I get to 3. I'm going to count 1, 2, 3. So prepare to snap your fingers like this when I get to 3, but don't do it. Don't actually snap. So now if you're preparing, you've got your fingers together like this. And what I want you to do is to pay close attention to what's going on in your head. Be very introspective and just see how it feels, and then we'll do the experiment and see what happens. So once again, you prepare to snap like this when I get to 3, but you don't do it. You just prepare. Okay, here we go. 1, 2, 3. How many of you snapped? Usually nobody does. Sometimes when I give a talk on this, 1 or 2 people might. Sometimes they do it by accident, they say, and sometimes they're just trying to cause trouble. But probably you didn't snap. So what was going on? Did you intend to snap your fingers when I got to 3? No, you didn't. What you intended to do is what I asked you to do, that is to prepare to snap them, but not to do it. And if that's right, then you weren't vetoing any intention to snap your fingers. You had no such intention. Something else was going on. So one thing that should make you wonder is, what does the new curve that I drew for you, that Libet got in the veto experiment, represent? And we'll come back to that later. Okay, so that is my presentation of Libet's main study, and then also the little veto study, which is a kind of sidebar but is relevant. And now I'm going to move on to the next study, study number 2. It was done with fMRI. What fMRI does is to measure changes in blood oxygen level over time. Or you can just think of it as changes in blood flow. But it's actually the blood oxygen that it's especially sensitive to. And In this study, subjects were in a brain scanner, and their task was to press either the left button or the right button whenever they wanted to. And after a lot of training, a lot of practicing and reading of fMRI scans, the scientists were able to predict with, this is a quotation, high accuracy, 7 to 10 seconds in advance of a button press, which button the person would press next. And so what they concluded is that the people were making their choices or decisions early and unconsciously, 7 to 10 seconds in advance of pressing a button, and they became aware of these decisions or intentions much later. So this is supposed to support Libet's idea that we make our decisions or intentions unconsciously and then become conscious of them after we make them. I want to describe the third study. It was done by Itzhak Fried and colleagues, and it was done using a different technology, the third kind of technology now, depth electrodes. So Libet used EEG. In the second study I described just now, done by Soon and colleagues, they used fMRI. And in this third one, they're using depth electrodes. Now, the background here is this. When people have severe epilepsy that can't be properly treated by drugs, occasionally they opt for surgery. And in order to do the surgery, part of the skull needs to be removed. And then they need to figure out where the surgery needs to be done. And so they place electrode grids on the brain and take readings. If subjects wish to, they can be participants in science experiments. And sometimes they agree to do that, and the experiments are done. Now, in this study that I'm going to talk about, electrode grids were used, and so readings were taken directly from the brain. The best readings you can get are directly from the brain, so these are really nice readings. So in this study, subjects are supposed to click a key whenever they want, and after lots of readings are taken, scientists are able to predict 800 milliseconds in advance of muscle motion within a window of 300 milliseconds when the person will generate the muscle motion. Now, what the scientists actually measure back from in this study, in the report of the study, is the W time. And the W time is the time of first awareness of the intention or urge or whatever, but that precedes muscle motion by 100 milliseconds, and it's easier for audiences to picture this in terms of muscle motion than in terms of the W time. So think about it this way. 800 milliseconds in advance of muscle motion, scientists are able to predict with 80% accuracy within a window of 300 milliseconds when that muscle motion will happen. And so the thought is something really important is going on about 800 milliseconds in advance of muscle motion, and 800 milliseconds is well before the average time of first reported awareness of the urge, intention, or whatever. So once again, we have evidence that people treat as indicating that decisions and intentions are made unconsciously, and people become conscious of them later. What I'm going to do is to describe 3 problems that all 3 experiments run into in moving from the data that they generate to the conclusion that there's no free will. And again, I won't be doing anything fancy philosophically. I'm going to concentrate on the data and what the data shows. So here's problem 1, the first problem shared by all 3, but we start with the Libet study. So recall that Libet thinks something very special happens at minus 550 milliseconds, that is a little more than half a second before muscle motion begins. He thinks that the special thing is that a decision is made then. Now, if that's right, one question we should ask is, how long does it take a decision to do something now, and in particular, to flex your wrist now, to generate muscle motion? If Libet's right, it takes a little more than half a second. But is that true? And what we should do then is look for separate evidence that would answer that question. How long does it take a decision to do something now to generate muscle motion when the muscle motion is wrist motion and you're flexing your wrist? Now, one way to get evidence is to look for reaction time studies in which subjects are watching one of these Libet clocks, one of these fast clocks. And the reason you want them to be watching a clock is that watching the clock is going to divide attention between that and the other task you're doing, which is the reaction time task. Now, in reaction time studies, subjects know what they're supposed to do when they get a go signal, and what they're supposed to do is do that thing as soon as they can in response to the go signal. So, for example, in a reaction time study in which the go signal is a tone, and what you're supposed to do is flex your wrist, your aim then would be to flex your wrist as soon as you can in response to the tone. So what I did, this was years ago now, I looked for a reaction time study in which subjects were using a Libet clock. They were watching a Libet clock. And I found one, and it was button pressing. So what subjects were supposed to do when they heard the tone was to click a button as soon as they could. And the mean time between the sounding of the tone and muscle motion was 231 milliseconds. So now, picture it this way. Suppose that what's going on is detection of the tone generates a proximal intention, that is, an intention to click right now. So you detect the tone, that generates the intention, and the intention generates muscle motion. So if the mean time between the sounding of the tone and muscle motion is 231 milliseconds, the mean time between intention and muscle motion is going to be a bit less than that, because it's a causal process of detecting the tone. Will take a little while to generate the intention. But now we're nowhere close to the 550 millisecond figure, and we are very close to the W time, the 200 millisecond figure. Now, when subjects aren't watching a clock and they're doing a similar reaction time test, reaction times tend to be shorter. In a study where subjects were flexing one wrist in response to a go signal, the mean time between go signal and muscle motion was 125 milliseconds. In a study where they're flexing two wrists, both wrists, in response to a go signal, the reaction time was even less. It was about 95 milliseconds. So what we have here then is evidence that what Libet is detecting at minus 550 milliseconds isn't yet a decision or intention to do a thing. It's something else, because if it were a decision or intention to do it right then, you'd get the movement much sooner than you do. Okay, so now we move to the soon study, and we ask what's going on at 7 to 10 seconds in advance of muscle motion or in advance of a button press. Now, I mentioned that the scientists reported that they were able to predict with high accuracy, that was the quotation, 7 to 10 seconds in advance which button the person would press next. The high accuracy was actually 60%, so 60% accuracy. Now, just to give you a feel for what 60% accuracy is, notice that with a fair coin, I can predict with 50% accuracy which of two buttons you're going to press next. So the scientists would do 10 points better in terms of accuracy, but I'm relatively close, 10 points lower. And also I can do better than make these predictions 7 to 10 seconds in advance. If you promise me that you won't press a button for a minute, then with my fair coin I can predict a minute in advance which button you're going to press next with 50% accuracy. So the 60% accuracy figure isn't enormously impressive, and I suspect that what's being detected is a slight bias toward one button or the other on the next press. And this is what I have in mind. What subjects need to do, what they're told to do, is not to fall into any patterns. So what they do then is they have to keep track, at least in a rough and ready way, of which button they've been pressing lately, what their patterns might have been, and try not to fall into any further patterns. And I believe that what happens then is that what's generated is a slight inclination for the left button, say, or the right button, that maybe the subjects are not conscious of. But if that's all it isn't a decision or an intention, it's just sort of a nudge. They're being nudged unconsciously in one direction or another, but not pushed all the way. So then in the Freed and co-authors study done with the depth electrodes, what's going on 800 milliseconds before muscle motion? Well, here too, I think that what's happening is that a process is up and running. Eventually it will result in muscle motion because what the person is supposed to do is click sooner or later. And, but when in the process is the actual decision to press now made? If we look at the reaction time studies, it's going to be close to 200 milliseconds before muscle motion. And I think the probability of raising or clicking soon rises as time goes by. But it doesn't rise all the way to 1. As far as we can tell, the evidence is just an 80% chance of muscle motion soon. So I think we don't have good evidence that decisions are made early, and the best evidence we have is putting the decision making much closer to the time of muscle motion, somewhere around 200 milliseconds before it. Okay, so that is one problem that all three studies have in common, and the short way to think about the problem is they haven't shown that decisions are made at these early times. The data are consistent with the decisions being made much closer to the time of motion and within that window of awareness time. So it's quite possible that the decisions aren't made until people are aware of making them. I move to problem 2. Here's a second problem that all three studies have in common. And it's a problem about the point of no return. So I have given talks about this sort of thing, and sometimes I do persuade people of my first point, that we don't have good evidence that decisions or intentions are made at the early times, and that they may well be made around 200 milliseconds before muscle motion. And sometimes I hear in response to that, well, okay, so maybe that's right, but even so, the point of no return is hit at these early times. Now, the point of no return is a point such that once a process hits it, it's just going to roll on to completion unless there's some kind of special interference. So their claim then is that once the brain gets to that point in the decision-making process, the point of no return has been hit. But that would mean that the point of no return has been hit before there's any consciousness of a decision and before there's any real decision. And the thought is, well, if the point of no return is hit back there before conscious deciding, then free will really isn't involved in the production of the decision or the action that executes the decision. That's the claim. So what we want to know now is the point of no return hit that early? So look at the purple box in the diagram. And one thing we'd want to know then is whether we have good evidence that, thinking about Libet's study in particular, that in that box, the point of no return has been hit. Now, how would we get evidence of that? We'd want to be able to look and see whether we ever get a curve that has that shape in that part of the box, but is not followed by muscle motion. So do you ever get a curve that looks like that but no muscle motion? That's what we'd need to look for. Now it turns out that given Libet's method in the main study, there's no way to look for that. And why is that? Because when you do EEG studies, you need to do something called back averaging. And so your computer needs to get a signal telling it to make a record of the preceding second or so of brain activity. And what Libet used as a signal to the computer to make a record of that activity was muscle motion. So it was only when there was muscle motion that you got these charts that you could read. But given that muscle motion is the trigger, you're precluded from looking for cases in which you get a curve that looks like that in the purple box, but no muscle motion. And let me just read you a quotation. Sometimes people think this can't be right, but it is. Here's a quotation from Libet on his method. In the absence of the muscle's electrical signal when being activated, there was no trigger to initiate the computer's recording of any preceding brain activity. So in other words, you can't look for what you want to look for in order to see whether the point of no return has been hit that early. Also, you can look for independent evidence of when the point of no return is hit. Now, my book, Effective Intentions, was published in 2009, and one study I suggested in that book was a stop signal study, and it was in connection with the point of no return. So if you want to know when the point of no return is hit in a process of the kinds we're talking about, one way to get evidence about it is to issue stop signals to people and move them closer to or further from the time you're interested in, and see whether there's time for people to stop a process in response to the stop signal. And the simple sort of study I suggested was this. You could tell subjects to flex a wrist when the spot or hand hit the 9 o'clock point on the clock, unless the clock face changed color from white to red. So at the start of the study, it's going to be white, and you can tell them, okay, now you can flex whenever you want, unless the clock face changes color to red, and then if it turns red, don't do it. Otherwise, do it. And what I predicted back then, because average stop signal reaction time is about 200 milliseconds, is that if you gave them 200 milliseconds or a little more, they'd be able to stop. So just picture a clock, picture the 9 o'clock point. Imagine putting a stop signal really close to that 9 o'clock point, like 100 milliseconds. That probably wouldn't do it. People are probably going to flex when it hits 9. But if you move it back to a little more than 200 milliseconds, my prediction was, people will have time to stop. Now, why is that relevant? Well, if they have time to stop, then they haven't really hit the point of no return in this process earlier. It can be stopped by an external signal. And if it can be stopped by an external signal, why not be stopped by an internal signal too? Just telling yourself, no, don't do it, wait for the next urge or whatever. So recently, there's a study done by Schulze-Kraft and colleagues. It was published in 2016. It's way more sophisticated than the one I sort of made up as an example back in 2009. And in this study, they use actual EEG readings to make predictions about when people will click, when they'll move. And they designed a stop signal study that is sensitive to real-time EEG. So they're predicting on the basis of the EEG when people will move, and then they're using stop signals based on those predictions, moving the signals around closer and further from the predicted time. And the signal they used was a red light. So the instruction was, it was like driving a car. So this is foot motions this time. The instruction was, after you get the green light, You can press that button on the floor whenever you want, but don't do it if the light changes to red. And what they discovered with their red stop signal is that if people, if there was no motion within 200 milliseconds of the red light showing up, in general there wasn't any motion. So that would be evidence that 200 milliseconds or so is enough to stop this process, which again is evidence that the point of no return is not hit earlier than 200 milliseconds before muscle motion. Now recall that the claim here that I'm countering is that even though decisions maybe are not made at those early times, the point of no return is hit at the early times, at minus 550 milliseconds, at minus 800 milliseconds, at minus 7 to 10 seconds before muscle motion. And what we have here is evidence that the point of no return is not hit until about 200 milliseconds before muscle motion, and that, as it happens, is right around W time, the time of first awareness of the decision or intention to do the thing in question. And now I move to the third problem. Now here, what I'd like you to do is to pretend that everything I said by way of criticism so far is false. Pretend that it's all false. Sometimes when I do this with audiences, I can see a look of despair coming over their faces, like, you mean it's all false? No, I think it's all true, but pretend it's false, and let's ask ourselves this question. If decisions and intentions really do come about at these early times in these studies, before people are conscious of them, would it follow that all decisions and intentions are like this? Because if these studies are going to threaten free will, they can't just threaten them in this little restricted domain of actions on which nothing hangs. They would have to apply to all decisions and intentions. And I want you to recall in this connection a quotation that I read to you earlier from Libet. It's the generalization quotation. Here it is again. Our overall findings do suggest some fundamental characteristics of the simpler acts that may be applicable to all consciously intended acts and even to responsibility and free will. Now, just to get a feel for what I want you to be thinking about, I want to tell you about my own experience as a subject in a Libet-style experiment. This was years ago. I gave a lecture to a motor control unit at the National Institutes of Health, and it was a lecture on free will and neuroscience. And the plan for that day was I would give my lecture, and then I would be a subject in a Libet-style study, and then they would take me out to dinner. So I gave my lecture, and it went well, I thought, and then it was time to be a subject in the experiment. So I sat in the chair, and I wanted to be a naive subject. So I wanted to just wait for the urges to flex to pop up and watch that clock and pay attention to where it was, where the hand was on it when I first became aware of the urge, and I wanted to flex in response to the urge, and then report after I flexed where the spot was on the clock when I first became aware of it. And by the way I reported back then was I just moved a cursor to the spot on the clock where I thought it was when I first became aware of my urge. So there I am, sitting in the chair, waiting for the first urge to flex now to arise. And what I discovered after a little time is that nothing was happening, that is, no urges were coming to mind. And I thought, my goodness, how do subjects do this? And then my next question to myself was, and what am I going to do to go through and complete the experiment so that I can then, have dinner? And what I did is I settled on the following strategy. What I would do is to say now silently to myself and to treat that now saying as an expression of a decision or intention to do the thing now, and then I would flex in response to it and try to keep track of where the spot was on the clock when I said now to myself silently. And the point I want to emphasize now is this, that when I said now to myself was utterly arbitrary. So I knew, I had to do it a fair number of times. And by the way, in these studies back then, you would always do at least 40 trials so that you could have readable evidence. You needed a bunch of trials so that once you did all the back averaging and so on, you'd get data that you could use. So I was saying now, 40 times over the course of an hour or so. But the precise time at which I said it was arbitrary. So what I was doing was randomly picking a time to say now. Now there's this old fable, the fable of Buridan's ass, and it's actually relevant here. So Buridan's ass was a hyper-rational donkey, and it was so rational, so hyper-rational, that it would never do a thing unless it had a reason to prefer doing it to anything else it might do at the time. And so one day the ass was wandering around wherever asses wander, and it found itself equidistant between two bales of hay. And the bales were equally large and equally attractive. And it was starting to get hungry, and it looked to the left, and it thought, boy, that's nice. And it looked to the right, and it thought, oh, equally nice. It looked back and forth, couldn't find a reason to prefer either to the other, and so what it did was to starve to death. Now, fortunately, we are not hyper-rational, and so we can just arbitrarily pick. Now, in the free will literature, so here's just a little bit of philosophy. In the free will literature, one of the views is called restrictivism. And according to the restrictivists, you're not in any position to freely choose, to make a free choice or exercise free will, unless you're torn between what you think you should do and what you're tempted to do. Or some other restrictivists will be a little bit broader and say, unless you're torn between either that or long-term self-interest and short-term temptation. But in the Buridan's ass kind of case, you're not torn in that way between things of different kinds. You just have to arbitrarily pick. And that's what I was like. And that's what all of these studies are like, all the science studies that I've been talking about. In all of them, you're arbitrarily picking. Now, either the restrictivists are right or they're wrong. If they're right, then none of these studies is even a study about free will, because they're all about arbitrary picking. But suppose that the restrictivists are wrong. Well, then the studies could be about free will, but even then we see how different arbitrary picking is from other cases of deciding. So think about decisions that are really important to you, that you think about for a long time before you actually make the decision. So for example, whether to propose marriage to a certain person now or to wait a while or maybe not do it ever, whether to accept a certain job offer when you have a good job already and you think it might be better but you're not so sure, whether it's time to go for a divorce or not. These things are not cases of arbitrary picking for the most part, so you put a lot of thought into it. And notice that the instructions in the neuroscience experiments shove consciousness aside except for the purposes of reporting. So you're not supposed to plan in advance when to flex or which key to press. You're not supposed to think about it. You're supposed to be spontaneous. But many of our decisions are not like that. They're preceded by conscious thinking. And it may be that the conscious thinking increases the probability of conscious deciding. So it would be very difficult to generalize from the supposition that in the studies I've been talking about, all the decisions are made unconsciously, to the claim that all decisions, even the ones preceded by conscious reflection, are made unconsciously. So now it's time to wrap it up, and I'll just sum up my conclusions. So the first thing I showed is that none of the studies provides good evidence that decisions are made at these early times, that they're made before the person is aware of making them. Second, none of the studies shows that the point of no return is hit at an early time. And third, even if the studies had shown that, we aren't entitled to move from a judgment that decisions are made unconsciously in those studies or the point of no return is hit early in those studies to the judgment that all decisions are made unconsciously, or whenever we decide the point of no return was hit before we made that decision. And those are the claims that are supposed to justify the proposition that we never decide freely. So all of these studies, in fact, leave it open that we do have free will. So what I have shown is that none of the studies I talked about shows that there's no free will. And I think in light of some of the things I talked about early on in this lecture, how some people's behavior got worse as a consequence of lowered confidence in free will, and of course the email I got, I think this is good news and we should be happy about it, and I'm closing on that positive note.
Hi, my name is Michael Murray. I'm a senior visiting scholar in philosophy at Franklin and Marshall College in Lancaster, Pennsylvania in the U.S. And I'm here today to talk to you about science and religion, the relationship between the two, and looking at some contemporary challenges that have been raised to religion from the domain of science. And to begin, I want to talk a bit about the history of the relationship between science and religion, and we'll begin with a story that's often been told about Galileo and the Catholic Church. So in 1615, Galileo was reeling from the first round of public condemnations that had been made of his views about astronomy. According to his view, the sun stands at the center of the solar system and the earth revolves around it and also moves on its axis. And as you might know, this was a view that was not widely held by the Catholic Church or, for that matter, by the Protestant reformers of the time. According to them, as they understood the scriptures, it's the earth that stands at the center of the cosmos, and everything revolves around it. Galileo was convinced that the empirical evidence showed otherwise, and he aimed to convince other people of that through his writings. But Galileo also regarded himself as a devout Christian, and as a result he was keen to find a way to reconcile his religious commitments with his newfound scientific discoveries. Now, his way of doing that was to conclude that the Bible just did not teach what the church authorities claimed. In fact, his view was that the Bible didn't aim to teach scientific truths at all. In fact, Galileo said in words that are often quoted, although not at the length that I'll quote them here, the following. Galileo wrote, "Since the Holy Ghost did not intend to teach us whether heaven moves or stands still, whether its shape is spherical or like a discus or extended in a plane, nor whether the earth is located at its center or off to one side, then so much less was it intended to settle for us any other conclusion of the same kind. I would say here something that was heard from an ecclesiastic of the most eminent degree, that the intention of the Holy Ghost is to teach us how one goes to heaven and not how the heavens go." The connection between science and religion is not just one of historical curiosity, as we might suppose if we focus just on the Galileo story, but one of substantial contemporary importance. Battles between science and religion are probably most well-known and most evident in the U.S., where that battle continues to be fought primarily between Christians of a conservative variety and scientists. But it's also true that these debates are going on broadly across the globe. They're being carried on both in public and privately in China, Russia, Israel, and in numerous Middle Eastern countries as well, where similar issues arise at the interface between Islam and science. So in order to know how to think about the connection between science and religion, we first need to know exactly what science is. We have to define our terms here clearly, because there are different ways of understanding it, and depending on how we understand it, we'll understand the relationship between science and religion differently. So we'll begin with a very minimalist definition of science, which is something like this. Science is the collective judgment of professional scholars who aim to explain the workings of the natural world through empirically testable theories. Now notice here I'm defining science not as a practice or as a discipline, since practices and disciplines won't have significant points of conflict with religion. Instead, we're defining science as a set of claims made by a certain sort of scholar who's engaging in a certain kind of work, those kind of work that scientists normally engage in. And thought of this way, there are three different ways of thinking about the relationship between religion and science, three ways in which you might think that they intersect. On one, we would say that science and religion conflict in principle. On a second view, we might say that science and religion cannot conflict in principle. And on the third view, the view that I'm going to defend, we could say that science and religion may or may not conflict. Whether they do depends on what those religious claims are and what scientists affirm. So let's take a look at these three views in turn. So on the first view, science and religion are in principle in conflict. So why would someone hold that view? Well, according to this view, the claims of religion and the claims of science are locked in conflict in such a way that only one or the other can survive. This is sometimes called the warfare model of the relationship between science and religion, a phrase that's been used since the late 19th century, taking its cue from a famous book that was published in the late 19th century. And this view was especially popular during that period and in the early 20th century as well, though there are many defenders of it today. One of those defenders is the famous Harvard scientist E.O. Wilson. He wrote a book a few years ago with the title Consilience, and Wilson puts it this way: acceptance of the supernatural conveyed a great advantage throughout prehistory when the brain was evolving. Thus it's in sharp contrast to biology, which was developed as a product of the modern age and is not underwritten by genetic algorithms. The uncomfortable truth is that the two beliefs are not factually compatible, says Wilson. As a result, he continues, those who hunger for both intellectual and religious truth will never acquire both in full measure. So what should we think about this view of in-principle conflict, the view that we find expressed in Wilson's writings? Well, first of all, there's something here on this view where the very definition of science and religion causes the conflict. But what are the definitions that are in play here? So some who defend this sort of model do so because they're adopting really quite contentious definitions of science and religion. For example, some claim that religion consists of beliefs that are drawn from purported divine revelations, and that these beliefs are held entirely on the basis of authority. So you believe those claims that come from revelation because you believe the authority of the purported revealer of those truths. Science, on the other hand, according to this view, consists of beliefs that are justified by sense experience and by the scientific method. So you might wonder, just given that characterization of the relation between religion and science, does it actually follow that they're in principle in conflict? And the answer is no, because it could be, given that characterization, that the same truth is revealed in whatever revealed text you take as authoritative. It might also be the claim that's being affirmed by scientists. So what do we have to add in order to draw the conclusion that science and religion are in principle in conflict on this point of view? Well, what we have to add is something that's really quite controversial. The principled conflict arises only when we add to this characterization of science that the only justifiable beliefs about the natural world are those that arise from sense experience and the scientific method. And when we add to the characterization of religion that the only justifiable beliefs about the natural world are those that are held on the basis of religious authority. The problem is those definitions don't seem to be very plausible, especially in the case of religion, holding that the only justifiable beliefs about the natural world are those that are held on the basis of religious authority. There are very few people who would affirm that that's a reasonable understanding of religion. So on this view, as a result, to accept the teachings of the Bible or the Quran about the natural world is to be anti-scientific, because it's not held on the basis of the scientific method, and to accept the deliverances of experience and the scientific method would be anti-religious, because on this view, the only justification for holding these views about the natural world is that they're revealed by a religious text. So if you were to hold this sort of view, then you really have to choose. It's science or religion. One can win only at the expense of the other. Some actually defend this model because they think it's a straightforward reading of the history of the relationship between science and religion. So you might take the Galileo affair as one example of this. Or even previously, it's oftentimes claimed, although this is not actually the case, that Christian figures, for example, held that the earth is flat, and science later proves that that's wrong. Or religion says that the earth doesn't move, and science later proves that in fact it does orbit the sun and rotates on its axis. Or religion says that the universe is less than 10,000 years old, and then science proves it's 14 billion years old. Or religion claims that human beings are directly created by God, and then science shows instead that human beings are descended from earlier primates, and so on. So you might think on this reading of the history, science and religion are locked in this kind of conflict because religious believers are committed to the idea that they're supposed to draw these claims about the natural world from Revelation, but in fact when the science comes along it shows them that these views are wrong, and so the two stand in this perpetual state of conflict. But as I mentioned earlier, it's not really clear that this is a reasonable way to characterize the relationship between science and religion. This is not a characterization which we should accept. Even if scientists were to accept that the only way to justify scientific beliefs is through sense experience and the application of the scientific method, it's worth noting that nothing from the domain of science justifies the scientist in that claim. That is, the claim that science alone provides us with justified beliefs about the natural world. That itself is an epistemological claim, a philosophical and normative claim, and not something that we could justify by appealing to sense experience and the scientific method. So there's something self-refuting about that way of trying to understand science. Second is that it grossly mischaracterizes the relationship between science and religion. So it's simply not true that the only way in which apparent conflicts between religious claims or claims from purported revelation and science, that the only way to resolve those conflicts is for religion to concede the point. And you can see this by looking at certain historical examples. So for example, in the early 20th century, the reigning cosmological model was something that's known now as the steady state model. And on the steady state model, the universe is eternal and not expanding. It's simply a static universe that doesn't change in any significant way other than movements of the parts. And many religious believers, especially those within the monotheistic tradition, struggled with the steady state theory because they believed that their religious revelation taught that in fact the universe had an origin in time. And so Christians, Muslims, and Jews who were confronting the steady state theory really wrestled with how to reconcile their religious beliefs with the science. And many of them concluded that they couldn't. That either this had showed that religious belief was false or that something was wrong with the science. And of course, what happened in the mid-20th century was that science in fact did change and came to the conclusion that in fact the universe had an origin in something we now describe as the Big Bang. Now of course scientists didn't reverse course on this point, didn't change their beliefs because they were appealing to religious revelation. But it simply shows that the relationship between these two are more complicated than this simplified historical narrative would lead us to believe. According to a second view, science and religion aren't in principle in conflict, but they're in principle non-conflicting. That is, there's something about religion and science that ensures that they can't possibly conflict. So how would someone develop this view? Well, there are a few different ways. According to one version, science and religion can't conflict in principle because they treat distinct domains of objects. So according to this view, science interrogates the natural world, the world of natural objects, atoms and molecules, stars and galaxies. Religion, on the other hand, speaks to what we might call supernatural objects. Religion purports to tell us about God or gods, angels, the supernatural, the afterlife, immaterial souls, and that sort of thing. Alternatively, one might hold that religion and science both concern the same domain of objects, but that religion concerns only one's experiences of religious reality in one's life, while science concerns the objects of our sense experience. So the famous 20th century German theologian Bultmann acknowledged that while religious revelations often make specific claims about the natural world, so the objects overlap with the scientific domain, these claims are religious only when they bear on ways in which human lives are transformed by theological modes of conceiving of human existence and meaning. So only when we attach a layer of religious significance to these natural objects do they come to fall into the domain of religion. So religious revelations aren't really about the natural world, even though they sometimes appear to be, even though they sometimes reference what we might call natural objects. So when we read something like in the Genesis text, God said, "Let there be light," and there was light, the text isn't affirming truths about cosmology, but rather telling us that God's the creator and sustainer of all that is. A second way you might argue that science and religion don't conflict in principle is to claim that they operate by different methods or with different aims. So it's not the objects that are different, it's the methods and aims. So for example, one might, adopting this model, might argue that the job of science is to determine what things the natural world contains and how those things behave. Science tells us about things like atoms and atomic theory, whereas the task of religion is to explain how God's providential purposes play out through the workings of the natural world. So in this view, science employs empirical observation and empirically testable theories to explain what there is, and the causal mechanisms that explain why those things act the way they do. But religion, on the other hand, uses religious revelation and maybe religious experience to discover the purpose and the meaning of the happenings in the natural world. This second version, according to which science and religion are non-conflicting in principle, has been defended probably most famously by the now late Harvard evolutionary theorist Stephen Jay Gould. And according to Gould, science and religion represent what he called distinct magisteria, where magisteria are sources of teaching authority. And they were non-overlapping in his view in such a way that science covers the empirical realm, what the universe is made of. He called that the domain of fact. And why those things work the way they do, he called that the domain of theory. Whereas the magisterium of religion extends over questions of ultimate meaning and moral value. So Gould says, to quote, while the magisterium might discuss a common object or topic, like cloning, for example, the methods and aims will be different. Science uses theory construction and experimentation to determine how cloning does or might work. Religion uses philosophical theorizing or appeals to authority to determine the moral boundaries in our use of cloning technology. So as a result, on this view, science and religion are these non-overlapping magisteria, and he designates this view with the acronym NOMA, non-overlapping magisteria, or NOMA as it's oftentimes called. So what should we think about Gould's view about the fact that science and religion are, or the claim that science and religion are in principle not able to conflict, non-overlapping? Well, for Gould's position to be tenable, two claims would have to be true. The first is that religion makes no natural or empirical claims. Because remember, for Gould, the idea is that religion talks about ultimate meaning and moral value, not matters of fact and theory. The second claim is that science can make no claims concerning supernatural reality or morality, because again, for science, it's just supposed to tell us what the natural world contains and how those things work. So are those two claims plausible? And the answer is probably not. First of all, in the first claim, that religion makes no natural or empirical claims, that seems to be pretty obviously false. When a Muslim affirms that Muhammad ascended bodily into heaven, or a Christian affirms that Jesus rose from the dead, they are making just such claims. They're making claims about aspects of the natural world and how that natural world behaves. Here's a real body of a real person, and here's what really happened to that body. Furthermore, when religious believers claim that certain things happen in the world by means of divine action, so creation or turning water into wine or parting the Red Seas, as a result of, again, some divine miraculous interaction, they are making a claim about what happened in the natural world. Here's what happened at the Red Sea. Here's what happened with this bit of water. So to make this claim that religion doesn't actually make any affirmations about the natural world just seems wrong. It looks like religious believers do in fact make those claims as religious claims. Of course, Gould might challenge that second part. That is, he might say that perhaps Muslims and Christians and others make these claims about the natural world, but they're not entitled to hold those as religious beliefs. That is, they'd have to hold those as scientific beliefs. But Gould really hasn't given us any reason to accept that claim. why would we have to hold, and in fact it would seem odd to hold, that for a Christian to claim that the resurrection of Jesus is not a religious claim? That would be really odd and not really an apt explanation of how religion actually functions. So what about the second claim? That second claim that holds that empirical observations or science can't tell us anything about the domain of morality or the supernatural. Is that right? Well, maybe it is, but certainly many people have challenged that claim. So many philosophers and some scientists think, for example, that we can draw inferences about the supernatural from the natural world. And here are two different sorts of examples. On the one hand, many people, and they don't have to be scientists or philosophers, think we can draw conclusions about the supernatural from the existence, for example, of natural evil, the existence of pain and suffering, or maybe pain and suffering that seem to be distributed in ways that aren't merited or justified or warranted in any way. That shows us that it can't be an all-good God. Some claim, now again, that's a contentious argument and it may be wrong, but it shows how one might make inferences from particular natural facts to certain claims about the reality of supernature or the supernatural realm. On the contrary, some have argued that there's evidence in the natural world that it displays a certain sort of fine-tuning, that the laws and constants seem to have been tuned in a way that makes it suitable to the emergence and existence of intelligent life. And some infer from that this looks like there's a teleology in nature that can only be explained if somehow a designer is involved in configuring nature in a certain way. Now, whether you take that argument seriously or not is not really the point here. The question is it possible for us, were we to discover natural facts like that, to draw inferences about supernature or divine reality? And it looks like in principle the answer is yes. And if in principle the answer is yes, then in principle Gould's claim about how science can function just isn't correct. So if it's not the case that science and religion are in principle in conflict, or in principle can't conflict, the conclusion we're left with is that science and religion are potentially conflicting. That is, there are some cases where science can make certain affirmations that contradict claims that people believe on the basis of religious revelation or religious experience, and vice versa. So how do we address apparent tensions between science and religion in those cases? And the answer is we just have to look at them on a case-by-case basis. We have to balance the strength of the evidence in favor of certain scientific beliefs against the strength of the evidence in favor of a conflicting religious belief, whether that belief emerges from a purported religious experience or from a revelation. So when we're in the process of engaging in this sort of balancing act, a religious believer, when there is tension with a certain scientific claim, really faces four options: to reject their religious belief, to reject their interpretation of the religious data, to reinterpret how they understand an experience or a text, to reject the evidence of their senses, or to reject an interpretation of the sense data and reject the claim that science has understood the data correctly. And you might wonder, well, is there one right answer to that question? Is there some default that we should hold as a religious believer? Should you always default to the science, or should you always default to the religious revelation? And actually some people think yes, but it looks like the best answer is probably no. That is, in each case what we've got is a body of data that we're interpreting in certain ways, and we always have to ask ourselves, where is the strongest evidence? Is the strongest evidence my interpretation of the text is clearly correct? And if I have reason to think the text is correct, that gives me reason to reject the scientific belief. And if I think the evidence in favor of a certain scientific claim is just undeniable based on the sense data, that will lead me to affirm that claim, perhaps in contrast to my interpretation of the religious text. So, on this view, science and religion potentially conflict. Now the interesting question is, do they actually conflict? And there are many purported cases of actual conflict between science and religion as well. So perhaps the one about which we hear the most is claims about human origins or cosmological origins, but there are many others. In many religious traditions, it's believed that the human mind is in some sense immaterial and capable of surviving bodily death. That view is not held in very high esteem by those in neuroscience and psychology, for example. So that's another case where we have to ask, how do we reconcile these two different sorts of beliefs? Of course, the classic example, as I mentioned, is one that concerns origins. For Muslims, Christians, and many others, the claim that the universe is very old, the claim that human beings are not separately created but descended from common ancestors. This assumes certain things. It assumes that the revelation that they appeal to is accurate, and it also assumes that their interpretation of the text is accurate. But when you see that, you see also that provides us with a recipe for resolving these sorts of challenges. And in order to resolve it, we first have to look at how these questions about origins are understood more specifically. And to do that, I'll turn to a taxonomy that was provided by the philosopher Alvin Plantinga. And Plantinga describes this potential conflict in terms of 5 distinct theses. And they are the ancient Earth thesis, the thesis of the universe and the Earth are billions of years old, which is a claim that has been apparently, or according to some, contradicted by certain religious texts. The progress thesis, that life has moved from simple unicellular organisms to complex multicellular organisms over time. The common ancestry thesis, that all terrestrial life shares a common ancestor. What Plantinga calls the Darwinist thesis, according to which the mechanisms that account for the diversity and complexity of life are those identified by evolutionary scientists, variation and selection, genetic drift, and so on. And fifth, the naturalistic origins of life thesis, the idea that life on Earth arose through purely naturalistic processes as opposed to a divine action or divine miracle. So critics of the evolutionary scheme of origins take issue with one, or in some cases with all of these theses. And these critics argue that the scientists have just misunderstood the data or mishandled it, or perhaps that there's an agenda behind their interpretation of the data that lead them to endorse those 5 theses. And as a result, they've fallen into error. But these critics have to also acknowledge that in the same way that our scientists have to interpret empirical data, they have to interpret the evidence of revelation in order to come to their religious convictions, and that perhaps those interpretations are wrong. So again, in the same way scientists are charged with the task of interpreting empirical data to come to conclusions, religious believers are charged with the task of interpreting a text. And the question then is, well, are there ever cases where the evidence shifts and we have some reason to believe that we should give more credence to one side or the other? And the answer is yes, on both sides. As religious believers engage in this balancing act, they need to realize that the evidence can change on both sides so that over time we can come to have a greater degree of confidence in a certain scientific claim. If you look at that list of 5 theses, you'll see that probably going from bottom to top, we have more evidence. So the evidence in favor of the claim that life arose by purely naturalistic means, it would actually be difficult to come up with evidence to show that. And we certainly don't have evidence of that now. So should the religious believer, if they think that their religious text teaches that life arose by some sort of non-natural process, should they give that up in the face of the scientific evidence? At this point, maybe not. But when it comes to the claim that the universe is 6,000 or 10,000 years old, in that case it looks like the scientific evidence is really very strong. And that should encourage religious believers to go back to the text and see if perhaps there's an alternative reading that's still consistent with what the text is trying to affirm. And that's in fact what's happened. In recent years, biblical scholars have returned to the biblical text and asked, can in fact we understand this text differently? And many think that in fact if we understand ancient Near Eastern literature and the creation myths that were present at the time, that in fact it should not be understood in the literal way that perhaps it has in the past. So when we understand that science and religion are in potential conflict, it puts us in this place of having to balance the evidence of one against the other, and our conclusions about which we ought to take most seriously at any given time is likely to change. Up to this point, we've been looking at the question of whether or not science and religion are or can be in conflict. But there's another set of questions that we could ask here, and that is it possible under any circumstances for science to provide support for certain religious or theological beliefs? So far from seeing science as this perpetual threat to religion, some scientists and philosophers argue that scientific discoveries actually provide us some evidence for the truth of certain religious claims. And that's a topic that you'll take up at other parts of this course, looking at particular cases where scientists and philosophers and others have argued that there are certain scientific data that supports religious beliefs. In this part of this talk, I'd like to look at something a little bit different. And that's the question of whether or not the scientific method itself might be seen to lend some support to religious claims. So let me explain how an argument like this might go. Think, for example, of a graph like this one, where we can show a bunch of data points that are plotted on a particular graph. We might take these points as being the conclusion of an experiment that we've done. When we look at this series of dots, you might ask, how should we sort of plot the line that provides the theory that explains how these different points fit together? And the most natural way for us to do that is simply to draw a straight line through them. If we were to be in a physics class or in a chemistry class, and we had a graph like this with a bunch of dots on the board, and we asked a student to come up and plot the graph for us, what they would most naturally do is to draw the straight line. But what if we had one student that came to the front of the class and drew a line that looked more like this? This squiggly line that seems to have all sorts of curves that, in one sense, don't seem to make any sense, given the dots that we have on the graph. Well, here's the question. I think when all of us see these two different graphs, we think probably, most obviously, the one that's closest to the truth is the straight line, not the very squiggly line. But why do we think that? Why do we think that the straight line is more likely to be a true explanation of how to understand the relationship between these two variables, the two variables on the graph, as opposed to the squiggly line? Well, that's a really hard question to answer. But what we know is true is that we do have this tendency to believe that simpler explanations, all other things being equal, simpler explanations are more likely to be true. Now, there's a lot to say about why we're disposed to think that way, but what it really boils down to is that there are two main options. Either we're disposed to think that simpler explanations are more likely to be true because evolutionary forces have wired us to favor these sorts of explanations, these simpler ones over more complex ones. Maybe evolution has wired us to favor simpler explanations because it takes less mental computing power to understand and remember simpler curves or simpler theories than it does more complex ones. But if that's right, if the reason we favor simpler explanations is because evolution wired us to do so, then we have to worry about what we're actually doing when we do science. Because what we thought we were doing was getting at the truth about things. But in this way of thinking about things, what we're doing is just sort of following the lead of evolved dispositions we have. And those evolved dispositions may or may not be leading us closer to the truth. Now you might think, well, look, there's another answer to this question. Maybe we just know through experience that simpler theories are more likely to be true. Or maybe there's some other argument in favor of the claim. But if you think that, I challenge you to try to articulate what those reasons are. Oftentimes when individuals are challenged with why we think simpler theories are more likely to be true, the reason that they'll give is something that just translates into because they're simpler, which isn't a very good explanation for holding that belief. So it looks like it defaults to, on the one hand, either we have evolved dispositions to come to believe that, in which case science is a very different enterprise than what we thought, or we need a different explanation. So what would that different explanation be? Well, one way to think about it is this. Rational beings, one of the things we think are characteristic of rational beings is that they tend to operate by the simplest means, all other things being equal. So if I want to walk from my living room to the next room over, which is my kitchen, I simply walk through the opening in the wall. What I don't do is climb up the downspout, climb in the window, or climb up onto the roof, descend down through the chimney, and walk through my living room to get to the kitchen. Why? Well, because there's no reason to do that. I would do it by the simplest means possible unless, again, there was some reason not to do that. So all other things being equal, rational beings tend to operate by the simplest means. Again, all other things being equal. Now, why does that matter? Well, if the universe is a product of a rational creator, then it would make sense that simpler theories are more likely to be true because rational agents tend to operate by the simplest means possible, all other things being equal. So if that's right, it gives us some justification for something that seems to be a very natural tendency that we have in the scientific domain. When we're looking at competing theoretical explanations, we tend to favor the simplest one. That's a puzzling thing, unless the universe is a product of a rational designer. So there we've got an instance where we're not trying to infer something about the supernatural or about the divine on the basis of some fact, the fine-tuning of the universe or cosmological origins, but we're looking at how we reason about science itself and whether or not that provides us with some reason to assume or presume that there's some sort of design or creator behind the reality of the cosmos. All right, so to conclude, we'll look at a couple of final challenges in the domain of science and religion. And the first I'll call a theoretical challenge. And one way to illustrate this challenge is to look at a quote from Richard Dawkins. So here's what Dawkins writes. The know-nothings, or fundamentalists, are, he says, honest. They're true to history. They recognize that until recently, one of religion's main functions was scientific, the explanation of existence, of the universe, or of life. Historically, most religions, says Dawkins, have had or even been a cosmology and a biology. I suspect that today, if you ask people to justify their belief in God, the dominant reason would be scientific. Most people, I believe, think that you need a God to explain the existence of the world, and especially the existence of life. They're wrong, but our education system is such that many people don't know it. So says Dawkins. So what we have in this passage from Dawkins is a challenge that you hear articulated by many people in many different ways, and we can think of this challenge in terms of a four-premise argument that goes as follows. Premise one, the only potentially good reason anyone ever had for believing in supernatural entities was the existence of some phenomena that could not be explained otherwise. Second premise, all phenomena that we formerly thought were explained by the activity of supernatural entities have now been explained in purely naturalistic terms. Third premise, so there are no longer any good reasons for believing in the existence of supernatural entities, so the conclusion is we should reject belief in those supernatural entities. So what should we think about this argument? Well, there are actually good reasons to challenge the first and the second premise of this argument. So the first is it true that the only potentially good reason anyone ever had for believing in supernatural entities was the existence of phenomena that couldn't be explained otherwise? And the answer is probably not. In fact, if you interview religious believers and ask them why they believe what they do, very few of them actually give you a scientific reason. Very few of them point to the existence of the cosmos requiring some sort of explanation, or the existence of life requiring some explanation. In fact, most of them will point to some sort of experiential evidence. Now, you might wonder whether or not that really undermines premise one, because you might think it's never the case that experiential evidence is good reason for believing, for holding some religious belief. But that itself is contentious. So, those who study the question of religious experience have argued that, in fact, it's very difficult to show disanalogies between religious experience and sense experience that give us good reason to favor the second but not the first. So if we have a sense experience of something, a cup being on the table, for example, our seeing that cup gives us good reason to hold the belief there's a cup on the table. Now imagine someone who has a purported religious experience. Perhaps they have a near-death experience in which they come to see the existence of what appears to be an all-loving, warm, welcoming light that they understand as some sort of a personal being. Should they take that experience seriously? That is, are they entitled to hold that what seems to them to be the case is in fact the case? And if you answer no, it's not, it's an answer that's very hard to justify, because it looks like that sort of experience should be given the same sort of presumption of innocence, or the presumption of truth until shown false, that our sense experience has. Now, there are certain challenges that have been raised to this line of reasoning. For example, some people will say, the reason I'm entitled to believe that the cup is on the table is because I can confirm it by a different sense, by reaching out and touching it with my hand. But even if we weren't able to reach out and touch it with our hand, if there was something that blocked us from having a second kind of experiential access to that reality, that probably wouldn't undermine our belief that the cup is on the table. If it's too far away for me to touch it, or for some other reason I can't get access to it, it still looks like I would have good reason to hold that belief. So likewise, some religious believers have said it could be the case that we have only a single modality that provides us with access to religious reality, and we should hold, again, that those beliefs on the basis of those sorts of experiences are innocent or presumed true until shown otherwise. So if that's right, that's a good reason to reject premise one. What about premise two? Is it true that all phenomena we formerly thought were explained by supernatural agents have now been explained by science? And the answer to that question is probably not. As I mentioned earlier, we really don't have a naturalistic account of the origins of life. That doesn't prove that supernatural origins are the right way to explain it. But that's not relevant here. What's relevant here is that premise two claims that all of these phenomena have been explained. And it looks like that's not true. But notice, even if it were the case that some of these natural phenomena that formerly were explained by appeals to divine action have been explained scientifically, that alone isn't a good reason to give up on religious belief, because it might be the case that rather than holding religious belief as an explanation for the origins of the universe, or the origins of life, or the apparent existence of fine-tuning in the cosmos, even if those things are explained naturalistically, one might adopt a religious hypothesis or a religious understanding of the world because it provides a global explanation for a variety of different types of belief. So, for example, perhaps the reason I hold to a religious belief, I hold to the claim, for example, that God exists and is the creator of all there is because I think it provides an overarching explanation for things like that there are objective moral truths, if you think there are objective moral truths, that it provides, that it's more likely to be true that there's a divine being in a world where there are immaterial souls, if you think that, in fact, there's good reason to hold that there are immaterial souls, or that theism is more likely in a world where we survive our bodily death, if you have reason to think that we do, in fact, survive our bodily death. So if we take a variety of different claims and ask, is there some overarching theoretical explanation that's more likely to be true if this suite of claims is correct, that might also provide us with some reason for holding to the religious hypothesis in contrast to the argument here. Let's look at one final challenge to religion that's emerged from science. And this is a challenge that's emerged from certain empirical data that's only come to the forefront in the last couple of decades. This is a challenge that's been raised from the domain of evolutionary psychology. So evolutionary psychology is a field of study that aims to understand the ways in which evolutionary pressures have shaped human cognition and behavior. Since religious beliefs and practices are pervasive across times and cultures, it gives us some reason to think that religion didn't just spread, but in some way was wired into our cognitive machinery. The reason it appears everywhere and across all times is because there's something just about the way that we're designed by evolution to come to hold these beliefs. So then one begins to ask the question, well, how would such evolutionary explanations work? How would evolution help to explain that we're wired in such a way that religious beliefs and practices emerge? Well, when evolutionary psychologists began to think about this, they thought this was really an especially puzzling way to try to explain the emergence of religion. And the reason for this is because so many religious beliefs and practices seem to harm our biological fitness. That is, religion seems something more like a Darwinian anomaly, because what you find in religious traditions is incentives for people to do things like rest rather than gathering more food or doing work to advance our fortunes, or providing significant sums of money to the temple or to the priest or to the church, when those funds instead could be kept for oneself as a way of advancing one's own fortunes. Taking vows of celibacy, for example, don't seem to enhance your evolutionary fitness. So how do we explain the emergence of religion when it looks like it contains all these fitness-harming practices? The challenge was put by the anthropologist Scott Atran in his book, In God We Trust, as follows. Religion is materially expensive and unrelentingly counterfactual and even counterintuitive. Religious practice is costly in terms of material sacrifice, emotional expenditure, and cognitive effort, in that it requires us to maintain both factual and counterintuitive networks of belief. So given all of its liabilities, is it really realistic to think that evolution can provide us with some explanation for why it's found across times and cultures? Now, I should pause and say, initially, something seems to be odd about evolutionary explanations of beliefs. The first time I think anyone comes to this topic, they think, well, I don't believe the things I believe because evolution wired me in certain ways. I believe certain things because people taught me stuff, or I've seen certain things happen in history, or I've engaged in certain kinds of reasoning, but it's not, evolution doesn't do anything to explain that. And while that might be true at the level of individual beliefs, the belief that George Washington is the first president of the United States isn't something you believe because of evolution, but it applies instead at a more general level. So think of it this way. We have certain kinds of cognitive equipment that wires us up in a certain way, that when we're stimulated, our senses are stimulated in certain ways, we form certain kinds of beliefs. I see the cup on the table, I form beliefs about cups being on the table. And I didn't teach myself to do that. I didn't learn to do it. No one said to me, when it looks to you this way, there's a cup on the table. I just reflexively form those beliefs. What specific beliefs I form, that might depend on the circumstances in which I'm in. So maybe something similar is true when it comes to religious belief. That is, maybe we're wired up in a certain way that we're led to form certain kinds of religious beliefs or to engage in certain kinds of religious practices when we're stimulated in certain ways. So what would that look like? Well, we know that the human mind is a cluster of cognitive tools. And these cognitive tools work together, collaborate in certain ways, that they generate certain sorts of beliefs. And according to certain theorists, leads us to form religious beliefs. So for example, these tools lead us to form beliefs in unseen agents. This is a phenomenon that we're all familiar with when we're laying in bed at night and we hear the loud bang noise in the closet. Right? What initially happens to us is that we have a fear response. We may get goosebumps, our respiration rate might increase, and we might wonder, who's in there, right? Who's in the closet? Well, it's sort of an odd belief to form just on the basis of a sound, but it's probably an evolved disposition we have to help us avoid predators. So we tend to infer the existence of unseen agents in the form of, in certain circumstances. Perhaps that's part of the cognitive mechanism that leads us to generate the belief in supernatural agents or in gods. It's also the case that these unseen agents, when we hypothesize unseen agents, we sometimes hypothesize the existence of agents that violate what seem to be certain innate cognitive expectations we have about agents. These are sometimes called counterintuitive agents in the evolutionary psychology literature. And what happens when we postulate the existence of these so-called counterintuitive agents is that they tend to be highly memorable. So when we think about the sorts of entities that we describe in folk literature, talking trees and so on, or invisible agents, agents that don't have bodies, these tend to be very memorable for us, and we tend to generate narratives about them. It's a truth about human culture that we're liable to generate narratives about these counterintuitive agents. So what evolutionary psychologists have claimed is that there are certain cognitive tools that we have that trigger certain kinds of beliefs, and when those beliefs form in certain sorts of ways, we tend to form narratives about them and to transmit those to others. And these are especially powerful when we attribute to those agents what you might call strategic information from which we might benefit, either because we're placating those agents or because it's providing us with strategic advantages with respect to how we interact with others. And maybe that strategic information is of the sort that when we act morally towards others, they'll act morally towards us. If these agents are able to communicate that sort of information to us, then it's valuable for us to have an awareness of them and to be involved in them in the way that religious rituals oftentimes describe. So there are many different theories, many different evolutionary theories about the origin of religious belief, and there's lots of data being collected that are aimed at trying to either help us confirm those hypotheses or disconfirm them. But for many religious believers find this sort of explanation threatening. And they find it threatening because they think it's provided an explanation for how evolution has caused these beliefs in us, even though they're not true. That is, that evolution in some way has tricked us into believing that religion is true. That's the conclusion that some religious believers draw. It's also the conclusion that some critics of religious belief have drawn. So what should we think about this? If these evolutionary explanations of the origin of religion are true, do they in fact debunk or undermine or disconfirm religious belief? Well, there are a few reasons to think not. So one is that, at least on the face of it, reasoning of this sort seems to commit a fallacy known as the genetic fallacy. So we know philosophically that we can't determine the truth or falsity of a belief simply on the basis of its origin. So I might come to believe that there are 137 people in the library because it's 1:37 on my watch right now. Now that would be a really bad reason to believe that there are 137 people in the library right now, but that doesn't mean it's false. So we can't draw conclusions about the truth or falsity of the belief just on the basis of the mechanism by which we came to it. Likewise, if this is the mechanism by which we come to hold religious belief, that doesn't show us that these beliefs are false. But some argue that it's not a matter of reasoning to the falsity of religious belief here. It's a matter of showing that it's unjustified. That is, you've come to hold these beliefs in a way that's not justified. So when you look at the watch and it says 1:37, well, there might be 137 people in the library, but you shouldn't think it. You shouldn't think it on those grounds. And in the same way, if you came to believe in these religious agents on the basis of these evolved dispositions, you shouldn't believe that either. That's unjustified. So is that correct? Well, maybe or maybe not. So imagine the following scenario. Imagine it's true that there is a God who created the universe and set evolutionary processes in motion in such a way that human beings like us emerged. Human beings with these dispositions to come to hold these beliefs. And let's also imagine it's the case that the divine being that created the cosmos and set these evolutionary forces in motion wanted that to happen. Wanted it to be the case that those mechanisms would lead you to have these belief-forming capacities that then led you to hold true beliefs about the existence of these supernatural agents. In that case, it would be as if someone in the library were beaming a signal to my watch to show 137 if there were 137 if there were 137 people in the library. And in that case, it looks like, in fact, perhaps the belief is justified. That is, the belief is tied to the target of the belief in the right sort of way that the belief might turn out to be justified. So what does all that really mean? What it means is, if in fact the universe is created in the way that theists claim, then even if these beliefs emerge through these evolutionary processes, they might perfectly well be justified. So if there is such a God, the beliefs are justified, and if they're not, they're not. Unfortunately, none of that really helps us to conclude whether or not those beliefs are justified on their own. It just takes us back to the initial question: is there such a divine being or not? So what I've argued here is that science and religion are positioned to engage each other. There's no way to know from the outset whether that engagement will be friendly or hostile. And as we've seen, the history of that engagement of these two domains has shown us really both sides. Religious believers, well, they'll continue to be in a position of having to negotiate the connections between these two domains of belief. And scientists will need to remain unprejudiced and open-minded about the potential religious implications of their discoveries and findings. But what it shows us, at least, is that the domain of inquiry concerning science and religion is a rich and fertile one, and one worth engaging in.
Hello, everyone. My name is Martin Kusch. I'm professor for philosophy of science and the theory of knowledge at the University of Vienna in Austria. And over the next 45 minutes or so, I will tell you a bit about relativism, and in particularly about relativism in the study of science. Now, we first need to get a rough idea of what we mean by relativism. And you might think that's easy enough to do, but like every ism in philosophy, so also relativism has many, many different meanings. Let me just give you a point of comparison. A famous American philosopher some 30 years ago or so published a paper entitled Realism. And in this realism paper, the author distinguished more than 80 different senses in which in the philosophy of morals and knowledge, the term realism is used. I would think that very much the same thing could be done for relativism as well. So even though I will give you now my definition, my shorthand definition of it, you should be aware of the fact that other philosophers might well not agree with that definition. So let me begin by giving you my definition. And rather than immediately jumping into the thorny issue of what relativism means in the study of science, let's first approach it through a case that perhaps it's more easy to appreciate. So let's take relativism in the domain of morals, of ethics. I think it's easier to see the structure of the relativist position there. So I think it's well documented that different cultures in different parts of the world have, at least to some extent, different moral principles that they seek to follow. So certain kinds of things might be allowed in one culture. We might go to such an extreme that in some cultures it's okay to kill your opponents and eat them, something which in other cultures would be abhorred, the idea. So cultures differ to some extent in the kind of moral demands they put on their members. Let that be the first element of the relativist position. The next thing is to say that the moral demands that cultures put on their members, addressed to their members, are relative to something. They are relative to the overall conception of morality that people have in different cultures. Let that be the second principle. The first idea was moral ideas differ, and the second, moral judgments differ, moral beliefs differ. And the second idea is that they differ in a systematic form, such that different cultures roughly come with different conceptions of morality. Let that be the second idea. The third idea now is the crunch of the matter. The third idea is to say that when cultures differ in these ways, and if cultures differ in these ways, then there is no way of putting them into an order of who is right and who is wrong. It's impossible to rank cultures with respect to their moral conceptions. In some sense, all these different moral conceptions are equally justified or equally unjustified. That's roughly the structure of a relativist position. So let's step back from the case of morality and try to formulate the idea a bit more generally. Morality is one domain in which we judge, but there are also other domains in which we judge. We judge, for example, about questions of taste. In aesthetics, we have the domain of knowledge. We have the domain of science. And maybe we have other domains as well, like the domain of religion. So the first element of a relativist position is to say, so there are these different domains, but with respect to each domain, we first of all find judgments people make in those domains. These judgments differ systematically with respect to different cultures, different background assumptions. And when we have those different background assumptions, these systems of rules by which we judge in those respective domains, then there's no neutral way of ordering these different conceptions as more or less correct. Let's work with that very rough idea of relativism to start with. That's the first thing that we need to know, that relativism is a general form of thinking about different domains. That also means, incidentally, that you can be a relativist in one domain and not be a relativist in another domain. So you might, for example, be a relativist about moral judgments, but not be a relativist about epistemic judgments, judgments on whether someone knows or not, or whether someone is justified in what they say or not. So you can be a relativist in one domain, you may not be a relativist in another domain. We all are probably relativists in some domains. Probably most of us would intuitively think that when it comes to questions of taste, at least in some respects, different judgments are equally justified. When we say things like beauty is in the eyes of the beholder, that's clearly an expression of a relativist sentiment. The idea is then that different viewers of the same painting might have different standards of what constitutes a good painting or a bad painting. And when that is the case, if we do believe that, there is no way of telling which standard is absolutely right and which standard is absolutely wrong. So we have different domains. You might be a relativist in some, you may not be a relativist in others. So that's an important distinction. In which respect are you relativist? But there's also another dimension in which different forms of relativism can differ, and that will be important when we think about relativism in science. And this is now the idea that you can be a relativist in a methodological sense, and you can be a relativist in a substantive sense. Let me explain. When you are a relativist in a substantive sense, then you are a relativist in the sense in which I've talked about it up to this stage. Then you think certain judgments in certain domains systematically differ, and they differ with respect to background assumptions or cultures, and there's no way of ranking those in a neutral way. So that's what we've talked about this far, substantive relativism. But you may also be just a relativist in a methodological sense, which means that when you study a certain area, then you study this area with a methodology that is relativistic. So, for example, if you are relativists in anthropology, then you might approach the study of other cultures on the assumption that there is no way to tell in a systematic way whether the culture's judgments, say about oracles or about witches, then you approach that discourse in this culture, the talk, the practices in this culture, without an evaluative stance. You approach the culture as if you were a relativist, as if there was no way of saying what they're doing is right or wrong. Even if though actually you do think they're wrong, you still approach them in your investigation without using the assumption that they are wrong. So let's just repeat this point once more, just to make sure that you have fully grasped the difference. So let's say that we have an anthropologist who goes into a culture in which they have witchcraft or believe in witchcraft, and they have certain practices around it. Say that they are trying to find out who are the witches amongst us. They are trying to persuade the witches to stop doing their witchcraft work, or in this way trying to neutralize the witches. Now, if you are a relativist and you study this witchcraft culture, how will you do it? Well, the most important thing about the relativist methodology is that you are trying to understand the coherence, the way in which the different assumptions of witchcraft fit together to form a harmonious whole without being contradictory in itself. You're trying to make sense of why do people think in this culture that witchcraft is a plausible way to think about the world or some aspect of their social world. That's the methodological relativism. You study witchcraft without actually evaluating it, and you actually think that the evaluative stance might be standing between you and a proper understanding of the witchcraft in that culture. The relativist investigator will think that your best chance of understanding what these people actually think is not to immediately turn on your evaluative instincts when you investigate the culture. Someone who thinks that a relativist methodology is a bad idea will say, well, we need to understand why these people can have such false beliefs. How is it possible for people to believe such nonsense? Or what ideology or what deception makes it so that people believe these things? That's precisely the kind of approach that the relativist anthropologist will not want. Okay, so we've talked a lot about relativism in general. I've talked a lot about relativism in general, and then about the different forms it can take, but we haven't yet mentioned science very much. So let me now try to apply what we have gone over in very general terms to the case of science. Now, the kind of relativism that has been most controversial in the study of science over the last 30 years or so has been methodological relativism. And it has come not so much from philosophy of science, the relativistic methodology, as it has come from the sociology of science. But both philosophy of science and sociology of science are part of what in general one calls science studies, or history and philosophy of science, history, philosophy, and sociology of science. So philosophers of science constantly negotiate and argue and debate with the sociologists and with the historians. So let me say a few words of what the sociologists of science have done. And it's actually very fitting for me to be talking here in Edinburgh about the sociology of science, the relativistic sociology of science, since that school was started in Edinburgh in the 1960s and then flourished in the 70s and 80s. Key figures in this movement were and are people like David Bloor, Barry Barnes, then Stephen Shapin, Simon Scheffer in Cambridge, and Harry Collins, and many others. Okay, so what did they do? I can make a direct link with what I've said about anthropology and what I will say about sociological study of science. Because the idea of the early work in the sociology of science was to say, we should do with respect to science what the anthropologists are doing with respect to witchcraft. We should study the history of science not by asking, how come those scientists in the past went so wrong in holding false beliefs that we no longer hold in science today, but we should rather try to understand scientific beliefs of the past against the background of the culture and the social arrangements prevalent in the cultures in which those scientific theories were developed. So the idea was, let's take what we have learned from the anthropologists and turn the anthropological gaze on science. This meant that sociology of science was not declaring winners and losers. It meant when the sociology of science looked at episodes in the past, the aim was not to say, look, great, the correct view has won, and let's celebrate this, as so much of traditional history of science, and indeed much of philosophy of science, did do and still does today. But the aim was let's try to understand why certain scientific views come to become prevalent in a given time period, and let's try to understand that against the background of what everything else people believed at the time. Let me give you a simple example that brings this home. Again, it's an example that links in two ways to Edinburgh. It links to Edinburgh because the historical case study I shall briefly summarize comes from a sociologist who was then based in Edinburgh, namely Steve Shapin. But the historical case that Shapin studied is Edinburgh in the early 19th century. In the early 19th century, there was a particular form of physiology stroke psychology popular in many places in Europe, but particularly in Edinburgh, and that was phrenology. Let me briefly explain the key assumptions of phrenology. Phrenologists wanted to explain differences between people. They wanted to explain why people differ in talents, and they wanted to explain why different societies are organized in different ways. And to explain this, they stipulated a number of distinct faculties in the human mind. And what was new there is that they were happy to stipulate a large number of such faculties. The traditional school philosophy that derived ultimately from Aristotle, from ancient philosophy, and then was further developed in medieval times, thought that there are but 4 to 5 faculties in the mind. There's judgment, there's the ability to form language, there is emotion, and some other faculties that were distinguished, but a very small number. What was strikingly new about phrenology is that it postulated a large number of such distinct faculties of the mind, between 25 and 35. So, for example, the phrenologist had faculties for competitiveness, a special faculty they assumed was central in the human mind and was responsible for our ability to judge our own standing in society, how we stand relative to other people, like the ability to scan whether one's social position is good or bad. That was an altogether new faculty in the mind that the phrenologist assumed. Then they also had faculties for musical abilities. They had faculties for different crafts that people might be able to do. They had faculties for different kinds of reasoning and much else beside. Additionally, the phrenologists linked the mind to the brain. The phrenologists thought that these different faculties that they distinguished, each had their distinct organ in the brain. So they thought the brain wasn't just one thing, one organ. Their brain, they thought, was a combination of many different organs. And each such organ housed one of those faculties. And then they took a further step. They assumed that the size of the respective faculty, or the degree to which one has one of the faculties, is explained by the size of the organ. So if you are very musical, they assumed, then this organ that is responsible for music at the back of the head would be bigger than in people who only have slight musical faculties. And then comes the last step. They thought that the different development of the organs would reflect itself in different bumps on the human skull. They thought that the shape of the brain influences the shape of the skull, and thus the trained phrenologist can read off the skull what someone's talents are. Now that sounds a quite bizarre theory to us today, though bear in mind that quite some influential contemporary forms of psychology also tend to think that the brain, not just in the brain, but that the human mind has what's nowadays called a modular structure, a structure of parts that can operate to some extent separate from the others. Okay, but let's leave aside for the moment the parallels to today's views. At first sight, it strikes us as a courageous theory, a bold theory. And one might think, so what explains that people believed that? And who was it who believed it? And who were the people who didn't believe it? Now comes the sociological analysis. So when Chapin analyzes this phenomenon of the popularity of phrenology in Edinburgh, he does not take the line of how can we explain that someone believed something so obscure, but he rather wants to explain why was it rational, perfectly rational, for people to be inclined to accept the phrenological views. Now, the first thing that Chapin draws attention to is that phrenology actually very closely engaged with the human brain. Phrenologists were the first people to actually cut up the brain in very, very fine slices and produced big atlases in which they drew these details of the brain that they discovered by cutting the brain in very fine slices. So they engaged very closely with the empirical material. That's one thing that impressed a lot of people. But there were also other factors involved that pushed or pulled certain people in the direction of phrenology. And very important in Chapin's explanation here is the class conflict in Edinburgh at the time. Edinburgh at the end of the 18th, the beginning of the 19th century, experienced a great social change and upheaval. The traditional landed aristocracy was becoming more impoverished, and there was a new class of people, tradesmen from the middle class or the bourgeoisie that were on the rise. The big social change was that many traditional divisions in society, like you had peasants and you had the landed aristocracy and you had a few guilds, became increasingly more diverse. You had many, many new professions. You had a whole new division of labor in society. Whole new lines of trade and production suddenly sprung up. The response of the traditionalists, the response of the aristocrats, was to say this new division of labor is unnatural. That's not how God has meant the world to be. The phrenologists said, no, that's exactly how God has wanted it to be, and that God has wanted it to be this way, you can see from the fact that the human brain is such that it supports a high degree of division of labor. The structure of the brain supports the idea of specialization that we see in the society that is emerging in front of our eyes. Why is that? Well, God has made it so that there are many different faculties in the human brain and in the human mind. And each of the faculty deserves its own specialized form of profession. That's the natural way to do it. The traditionalists said, no, that's not the natural way to do it. There are just 4 or 5 faculties in the mind, and it wasn't meant to be that way, that we have all that specialization and division of labor. But the bourgeoisie thought that's what phrenology shows. Phrenology shows us that division of labor to the degree that we see in front of our eyes is natural. So let's step back of this and ask ourselves, what does that have to do with relativism? Let's just repeat the central message. Chapin is saying, when we study science and when we try to understand why certain scientific theories become accepted, it's not enough to look at the theories in isolation. It's not enough to just look at the evidence, what does the brain look like, and the theoretical beliefs. In this case, the brain has this structure of a combination of many organs. That's not enough. To understand why a theory is developed in a certain way, and to understand why a theory is accepted, we need to understand the whole scientific community in its social context. The social context of 19th century Edinburgh needs to be taken into account when we want to explain why phrenology became an important and influential theory. So Chapin says, let's not evaluate phrenology. Let's try to explain why it became the dominant theory. So this is a methodological relativism. It's a relativism which says, in order to understand how science works, you had best not try to evaluate it at the same time. Of course, you can have your evaluations, but don't keep your evaluations away from trying to explain why scientific theories become accepted. Okay, so I've given you one key example of how a relativist methodology in science looks. Let's develop this a little bit further and ask ourselves, so why was this perceived as a threat or as a challenge, we might say, to the philosophy of science? Some philosophers of science saw it as a threat because they felt that what is most valuable about science, namely scientific rationality, is somehow pushed into the background. Some philosophers felt that when we as philosophers, or in general, when we as historians of science even, look at the past, we should always think about the scientific past in evaluative terms, where this evaluation, the standard for this evaluation, is rationality, is scientific rationality. And then different philosophers of science have different theories about what that background rationality might be. So some people thought, like Popper, for example, that scientific rationality consists in testing theories under the harshest possible conditions in an effort to refute them. And if you can't refute them, then you're allowed to stick with them for the time being. But it's a mark of scientific rationality that you always put your theories under the most severe tests. Chapin is saying that's not exactly what happened in the phonology case. The phonologists did not go out trying to refute their own theories. They felt, in light of what they saw about their society around them, it was a very well confirmed theory and it didn't need any further harsh testing. So by Popper standards, they were doing bad science. So Popper would say this phonology case, to properly analyze it, is to analyze what went wrong there. What went wrong is that it wasn't sufficiently put under harsh and severe tests. So a Popperian would think that a relativistic approach to the history of science misses what actually characterizes science. For philosophers of science of Popper's ilk, let me repeat this point, to study science in a relativistic spirit is to miss what makes science science. It would be like as if we studied science as if it was some other cultural phenomenon, like taste or fashion. We only see science as science, on a Popperian view, if we evaluate the rationality of the given scientific episode. So here you have a sharp line against any relativistic approach to science. At the same time, though, it should be said that even within the philosophy of science itself, and certainly within history of science more broadly, there were other approaches that were at least to some extent in harmony, or at least more sympathetic towards the relativistic line coming from the sociologists. Of particular importance here is the work of the philosopher and historian of science Thomas Kuhn, who in his famous book, you probably have heard about this in other units, The Structure of Scientific Revolution from the early 1960s, developed a theory about the way in which science develops. Perhaps it's appropriate that I remind you of one or two features of Kuhn's view so that we can then see both the commonality in some respect and the differences with the sociological view. So here's how Kuhn thinks about science. Kuhn thinks that science develops in a cyclical form. Kuhn thinks that once science becomes mature, it develops in a cyclical form in the sense that the same pattern repeats itself over and over again. So let me take you briefly through that pattern. The starting point of that pattern is a phase that Kuhn calls normal science. Under the conditions of normal science, in a given scientific discipline, scientists in that discipline share a number of assumptions and techniques about the fields, about the phenomena they are studying. Kuhn calls this set of shared assumptions a paradigm. So a paradigm for Kuhn is something that defines a scientific community. You have a scientific community insofar as you have a number of people who share the same paradigm, meaning they share the same assumptions about how the phenomena for that field are to be studied, what methods are to be used, what kind of theories do we want to achieve. Do we want them to be formal theories, mathematical theories, using mathematics? Or do we want a more qualitative, less mathematical approach? What kind of instruments should be used? And what kind of exemplars exist for the study in this field? By exemplar, Kuhn means an exemplary achievement in that field of science. So go back to the to the chemical revolution of the 18th century, just to have an example. There, famous influential French scientist, Lavoisier, came up with a new idea of how to study chemistry. Lavoisier said, the only way to properly study chemistry is to be able to measure. if you can't give a mathematical characterization of the processes you are studying, you are not really doing chemistry. Chemists before Lavoisier did not think that was important. Chemistry before Lavoisier was mainly practiced by pharmacists that, interestingly, in Britain are still often called chemists. So the first chemists were the pharmacists. And the pharmacists were not interested in mathematical characterizations of the interaction of different materials. They were interested in mixing materials so that they would have a beneficial effect on someone's health. So Lavoisier introduced a new paradigm. Lavoisier suggested we have to put chemistry on a whole new footing. You have to have complicated machines, big machines. He was doing big science by the standards of the time. And incidentally, the only reason why he could do it was because he was a tax collector. And most of the money that he collected in taxes for the king went straight into his own pocket, which soon made him one of the richest people in France. And that enabled him to run what we nowadays would call high-tech experiments that were hugely expensive. So by doing this, Lavoisier set a new standard for chemistry. He introduced a new paradigm. He said, from now on, let's use these complicated, expensive machineries. Let's have mathematical characterizations of what we are observing and seeing. And let's not be pharmacists anymore. We want to be like physicists. We want to gain pure knowledge. So what I've characterized for you here is a paradigm, Lavoisier's paradigm. So that's normal science. You have like a phase in which people share the same paradigm. But, says Kuhn, if we look at the history of science, it's also striking that while a paradigm is influential and powerful for a time, it's not able to explain everything. There always will be phenomena that a given paradigm cannot explain. For example, it was a big problem for Lavoisier's chemistry that he wasn't actually able to measure everything that he was claiming to be measuring. For example, he introduced one element, caloric, which he was not, like the element of heat, that he was not able to quantify. That was a big problem because he demanded everything should be quantifiable. But then he couldn't even quantify his own favorite element. So every paradigm over time encounters more and more things it can't really explain. It encounters more and more anomalies, as the technical term goes in Kuhn's work. And as those anomalies build up over time, there comes a point when the scientific community in question somehow thinks it just can't go on like that. We can't be piling up more and more anomalies. There must be something wrong with our paradigm. And then Kuhn thinks when that happens, we enter a new phase in the cyclical process, the phase of a crisis. When like scientists in that field literally feel they are losing the ground under their feet. They don't quite know anymore what to do, how to go on. Eventually, during this period of crisis, a number of new paradigms, new ways of doing chemistry or physics, what have you, are new ways of doing this kind of research. And then eventually the scientific revolution ushers into a new phase of normal science. Now, Kuhn's have often been read as a form of relativism. How is that possible? Well, Kuhn said that different paradigms, even within the same scientific discipline, different subsequent paradigms, have usually different standards of what constitutes good science. Such that the old paradigm, from the perspective of the old paradigm that is replaced by the new paradigm seems clearly wrong. And from the perspective of the new paradigm, the old paradigm looks clearly wrong. So each has its own idea of how you really ought to do science. I mean, for example, before Lavoisier's chemistry became dominant, there was another form of chemistry, the structure around the phlogiston theory. The details don't really need to be important for us now. But the important point is that from the perspective of the previous chemistry, what Lavoisier was doing wasn't particularly sensible. It didn't really make sense to think that chemistry should be like physics. Why shouldn't chemistry be like pharmacy? Isn't that the heart of chemistry? How can this man come with his big instruments and say everything has to be quantifiable from now on? Why should we accept that? Whereas from Lavoisier's perspective, what the people before him doing wasn't even really science. So then who is right? Well, from the old perspective, the old paradigm is right. From the new perspective, the new one is right. And Kuhn seemed to suggest that there is no neutral standpoint that would decide who is really right. And that, of course, should remind you of relativistic themes. Remember our initial characterization. In the same domain, here the same domain of chemistry, we have different judgments based on different background assumptions, and there's no way to say which one is really right. The one is right from its perspective, the other one is right from that perspective. So clearly there is a relativistic theme in Kuhn as well. Kuhn realized that, but was very uneasy about it. And he said, well, maybe there is a way to, after all, say which one is a bit more right, because there are certain virtues that we attach to scientific theories. For example, we want scientific theories to be as simple as possible. We don't want them to be too convoluted. We want them to be structured, simple, straightforward. We also want that the scientific theory covers a lot of ground. We want that the scope of the theory is broad. We want it that it's successful in its explanation and other things as well. And he thinks maybe there is a way with these kind of virtues to say who is a bit more right than the other. His critics immediately pointed out that none of these virtues that he was identifying was particularly neutral. Take, for example, the virtue of simplicity. Simplicity is a bit like beauty. It's in the eye of the beholder. Certainly the phrenologists thought, the chemists before Lavoisier, that their theory had the virtue of simplicity. Lavoisier thought that his had the virtue of simplicity. Think of it also this way. When is a theory more simple than another? If it has less laws in it, less laws of nature in it, or if it postulates a smaller number of entities. Is it more simple if the overall theory can be more briefly stated? Or is it more simple if it can be stated in ordinary language rather than in technical language? So simplicity doesn't seem to be something that is really neutral between scientific paradigms, but might itself be interpreted differently by different scientific paradigms. So it seems like the Kuhnian model is itself rather relativistic. So what did Kuhn then say when he encountered the sociology of scientific knowledge? Did he say, hooray, I have an ally? I'm not the only one with a relativistic approach to science. There are other people as well, the sociologist of scientific knowledge. You might think that he should have said that. And the sociologists of scientific knowledge certainly saw Kuhn as an ally. They said, one of our central background figures is Kuhn. 3 cheers for Kuhn. Kuhn wasn't impressed. Kuhn said, sociology of knowledge is deconstruction gone mad. Never mind what deconstruction is. It was at one time a very fashionable form of philosophy coming out of France that amongst certain Anglo-American philosophers was held in disrepute. So to say that sociology of scientific knowledge is deconstruction gone mad was just one long swear word. Why did Kuhn say that? I think Kuhn said that because notice one important difference between Kuhn and the sociology of scientific knowledge. The sociology of scientific knowledge tries to explain why a scientific theory is accepted by placing that theory into its broader social political context. Shapin explains the success of phrenology by saying, well, look at the social structure and the social battles in Edinburgh at the time. There's no way to understand science unless you place science in society. But that's precisely the move that Kuhn refuses to take. Kuhn says, no, we only should look properly at science itself. We should look at how scientists are organized around a paradigm. We should look at how anomalies start building up. We should look at scientists' responses to the anomalies. We should understand how they feel they lose the ground under their feet, and how eventually, in ways that are hard to make fully explicit, they come up with a new paradigm. But Kuhn does not try to explain the emergence of a new paradigm by placing the science into its broader society. So therefore, ultimately, we have here two rather different forms of relativism in the study of science. Both have a methodological kind of relativism about them. Kuhn is not really evaluating the theories in the history of science he looks at. That is common ground. He's also a methodological relativist, at least. But they differ in what position they give to social political factors in the explanation for change and stability in science. So it's important for you to understand that relativism in the study of science is not one view, it's at least two views, namely Kuhn on the one hand and the sociology of scientific knowledge on the other hand. There's also a third line that's worth at least mentioning, and this third line lies somewhere between Kuhn and the sociology of knowledge, and this is the work of the Austrian philosopher Paul Feyerabend, who, roughly the same generation as Kuhn, developed his ideas pretty much in tandem with Kuhn, and there was much common ground between them. But Feyerabend pushed Kuhn's ideas in a bit more radical fashion forward. Let me just explain a couple of his central ideas. One idea can be captured in a slogan that is often associated with relativism. And this is the slogan, anything goes. What did Feyerabend mean by it? Or before I actually say what Feyerabend meant by it, I should say that whenever people want to criticize relativism quickly and want to explain that relativism is an utterly implausible, indeed pernicious view, they often say something like, oh, relativism must be wrong. It's just not true that anything goes. So this formula, relativism equals anything goes, in some respects is treated most often as a stick with which to beat all relativist positions, rather than that people really try to understand and try to get to the heart of it. What did Feyerabend actually mean by it? So let me give you a very brief characterization of what I think Feyerabend meant by it. On a traditional picture of science and the rationality of science, scientific work, rational scientific work, is the application of general rules of good science to particular instances. I've given you an example of such a general rule of good science, namely the Popperian rule, according to which good science consists in putting your theories to the harshest possible tests, never believing your theories fully, because you always think, well, I can only believe it provisionally. I can only say, well, so far my theory hasn't yet been refuted. but I'll keep trying to refute it. That's the Popperian central methodological rule. Feyerabend was a one-time student of Popper, and he reacted first and foremost against the Popperian ideal that to be rational in science, to exercise scientific rationality, is to apply these general methodological rules to specific instances of scientific work. What Feyerabend tried to show against Popper, like he took a number of Popper's general methodological rules and tried to show that important advances in the history of science generally, of course, consists in flouting those rules. Feyerabend tries to show that in important episodes, like Galileo's famous experiments, the genius of the scientific experimenter and theoretician often lay in the systematic disregard for those rules of science. So the slogan "anything goes" means any rule of method that a philosopher of science has ever formulated can be shown to be dysfunctional in some historical episode or other. Scientific rationality simply isn't the application of those general rules, but scientific rationality is the ability to judge particular instances, particular challenges, and try to determine for that specific case how to proceed, where those general rules may be somewhere in the background or play in fact no role at all. That idea in itself need not be relativistic. But Feyerabend was very skeptical with respect to all general absolutes in science. I've already characterized this with respect to the methodological rules. No methodological rule is valid in anything like an absolute fashion. Every rule can be flouted. And therefore Feyerabend also thought that it's very hard to give general principles in terms of which we evaluate the history of science. There can be no general framework that gives you the platform from which you can judge scientific work in different periods as either falling on the side of rational or the irrational. To understand what scientists did, you really have to go into the nitty-gritty of the challenges that they were facing. Feyerabend took a very broad brush view to the history of science ultimately, whereas the sociologists of science and Kuhn over time went into ever greater detail with respect to scientific episodes. Shapin started with the phrenologists, wrote a couple of papers on it. Later he studied the work of the physicist, chemist Boyle in great detail in 2 books, actually 3 books. He also wrote a short introductory books on it. So the sociologist's tendency was to go into ever greater detail in specific episodes. Kuhn actually did the same thing. After he wrote this programmatic book, The Structure of Scientific Revolution, he later wrote a big historical book about an important episode in history of quantum mechanics, where he went to excruciating detail in trying to explain specific decisions scientists made. So they went into ever greater detail. Feyerabend somehow zoomed out of the details more and more looked at the history of Western thought from antiquity to the present. And he took a very relativistic view on that history. He didn't think that we had any right to judge that we now have got it right. We now got the rational view on how to study the world, but in the Stone Age they had it all wrong. He tried as hard as he could to identify, even in Stone Age, engagement with nature, a critical spirit, a critical engagement with the natural world, even an experimental attitude. He studied witchcraft. He studied medieval systems of predicting behavior in terms of astrological ideas. And he tried to explain the rationality even in those kinds of moves. Mind you, though, Feyerabend never quite went the sociological direction either. He never really tried to explain scientific results or witchcraft or any of these phenomena in terms of the broader social, cultural phenomena. He tried to do that to some extent, but never to the extent in which the sociologist of knowledge did it. Feyerabend also made another interesting move that became like a signature feature of his thinking, his relativistic thinking. And this is the parallel between science and art. Feyerabend was a very cultured, very educated man, as most people who grew up in Vienna, even if they don't want to, end up that way, simply because for the rich cultural heritage in the city. So he knew his medieval art, he knew his early modern art, he knew a lot about music as well. And so he studied in some detail the cognitive character of art, artists' engagement with the world, and then tried to show that scientific way of approaching the world is not as completely different as, say, a Popperian view of science would make you believe. On the Popperian view, you would say, which artist would ever have tested their artworks? So it's clearly different than science. Whereas Feyerabend tries to show how experimental art in Dürer and other people who experimented with perspective could be, and how many interaction there has been in the past between, say, painting and scientific theorizing. Okay, so I've given you a general characterization of relativism in science, and I've put much emphasis on the methodological side to that relativism in the study of science. I've explained to you why some scientists, for example, Popper, would oppose this view of science. And I've also explained to you two relativistic directions that emerged within the philosophy of science itself. So I've told you quite a bit about the past. Kuhn wrote this book in the early 1960s. Many of Feyerabend's writings were most influential writings of the 70s, 80s, and 90s. The sociology of scientific knowledge keeps going to this day. But you might well wonder, so where does the future lie? What are the new challenges for relativism? Does relativism have a future in the study of science? And what are its opponents? Well, let's start with the last question. What are the opponents of relativism? Well, if you look at the literature in philosophy, you might think that there are very many opponents. Sometimes the central opponent of relativism is described as realism. Sometimes the central opponent of relativism is called rationalism. And sometimes the general opponent of relativism is called absolutism. And I think we need to understand a little bit the meaning of those terms that relativism is opposed to, allegedly, to also get a clearer handle on the debates around relativism. Let's start with absolutism. Absolutism seems the most, at least terminologically, the most important opponent of relativism. Something is either relative or absolute. If it's absolute, it isn't relative. That seems to mark a very clear opposition. But there are many philosophers who don't want to be characterized as absolutists, because to be characterized as an absolutist seems like as if you had somehow captured the absolute truth about something, or as if you thought the absolute truth about something even could be captured. So relativists like to characterize their opponents as absolutists very often. And this, of course, done with the rhetorical effect of putting their opponents in a position that they don't really want to take in the first place. So it may be a little artificial to oppose them in this way. People who oppose relativism don't tend to call themselves absolutists, but more tend to call themselves either rationalists or realists. When they call themselves rationalists, They want to put the relativists on the side of something which is not rational. It then becomes you are either rationalist or you are relativist, and since the opposite of rationalism is irrationalism, by definition, if you're a relativist, you're also an irrationalist. That kind of fits with the way in which Popper thought. Popper thought he's a rationalist. He called himself a critical rationalist. And so the sociology of knowledge, insofar as it refused to do what Popper was doing, in Popper's eyes, was irrational. Now, obviously, that's not a characterization that the relativists find very appealing, so they reject that characterization. So again, we feel like it seems like the two sides don't really meet. Each side uses for the other side a term that the other side doesn't really want to accept. We have the same problem with respect to realism. I mentioned when I started that there is this famous paper by Susan Haag. Now I remember her name, I didn't remember it at the beginning. Susan Haag's paper distinguishing these 80-something meanings of realism. So if we now oppose realism to relativism, the question becomes, well, what do we mean by realism? And even the realists in philosophy of science are not agreed what they agree on. So let's make a very simple characterization. Let's distinguish between two characterizations of realism. One characterization, let's call it basic realism. Let basic realism be the view that there is a world independent of us. There's a world outside my mind that has the structure it has independently of my mind. Even if I had never existed, indeed even if no human had ever existed, many central features of the world would be what they are, independently of us. Call that basic realism. Let's distinguish from that a second form of realism. Let's call that ambitious realism. Let ambitious realism be the view that there is a world independently of our thinking, and that world has a specific structure, and that scientific progress consists in getting ever closer to that structure. This view is also sometimes called scientific realism. Let's just call it ambitious realism, to have the contrast between basic and ambitious. Now, how does the relativist stand with respect to those characterizations? I have yet to encounter a relativist who is not a basic realist. Relativists don't say there is no mind-independent world. I mean, that would be a view that in philosophy sometimes is called idealism. The world is just our projection of some sort. There is no mind-independent world. The world is just as we or God's mind project it. Relativists in this day and age, and in particular relativists with respect to science, don't hold such kind of view. So in that sense, they are realists. Most of them, though, are not realists in the ambitious realist sense. Strictly speaking, you could be a relativist and even be a scientific realist. You could accept that in some way or form reality has a structure independent of us, and that in some sense we get a better handle on some aspects of that structure, while still accepting the kind of studies that the sociology of scientific knowledge does. Kuhn, for example, to take another case, does think that there is progress in science. He just doesn't speak of it as us coming ever closer to the ultimate structure of reality. He rather prefers to turn it around and say, well, there is some progress in that we eradicate more and more of our mistakes. But of course, if we eradicate more and more of our mistakes about nature, there is some sense in which we make more contact with nature. So realism, if we want to contrast it with relativism, is a complicated issue. We need to be very clear on what we mean by realism in order to actually even achieve a contrast with relativism. I'm not going to here try to tell you now how should we really think about the contrast. I think what I most want to sensitize you for, that it's difficult with this ism, as with many other isms in philosophy, to even state clearly and to work out for oneself just how it is to be distinguished from other positions. What are the other positions that it is in tension with? and what are the other positions it can be combined with. But the thing that I want you to take away from these comparisons, that relativism is not the same as irrationalism. The relativist that we saw in the study of science does not say that the phrenologists were irrational. The relativist is trying to understand, why was it rational for people of the bourgeoisie in Edinburgh to find phrenology so convincing? So it's not opposed to rationalism. It's opposed to Popperian-style rationalism, where it means we have clear rules of science that are true everywhere. But it's not irrational in the sense that scientific choices are completely arbitrary. Anything goes. You can go any way you like. It doesn't matter. Relativism allows for everything. That's not the view. Nor is the view that relativism equals irrealism or anti-realism. It doesn't need to be that way. It need not be opposed to basic realism. And it may not even be fully incompatible with stronger forms of realism. That's very much an open debate here and now. Okay, so where do we go from here? What are the next important philosophical issues concerning relativism and the philosophy of science? This, of course, will be very much a statement of my own view, because philosophy is an area of disagreement and contestation. And so just like as there are as many relativists or realists almost as there are philosophers advocating those positions, there also, of course, are as many different views of where we go from here. So let me just say where I think interesting challenges for the future lie. First of all, it's important to emphasize that philosophy of science has developed hugely from the days of Popper. I've used Popper here as an easy foil to set up the contrast between sociology of science and philosophy of science. But of course, today's philosophy of science is in many ways much more sophisticated than Popper's views were, or even Kuhn's views were, and that in several ways. The first way in which philosophy of science has changed tremendously over the last 20, 30 years is that it has learned a few lessons from its opponents. It has learned, for example, from the sociologists and the historians that to do good philosophy of science, you have to engage with the details of scientific work. You cannot write the philosophy of science by, at most, looking at science textbooks. To understand the dynamic and theory choice in science, you have to do case studies, detailed observation. You have to look at the letters, you have to interview. You have to look at the emergence of a scientific theory in order to understand the dynamics of the development of science. So philosophy of science has become considerably more empirical. That's the first thing. The second thing is that philosophy of science has become less insulated. It used to be the case that philosophers of science had relatively little interaction with other areas of philosophy. So, for example, for decades, philosophy of science and epistemology, the study of knowledge, have, surprisingly enough, lived pretty separate lives. Philosophers of science have ignored what the epistemologists did. Bad. But epistemologists have just as much ignored what philosophers of science was doing. I recall, for example, the statement of a very influential contemporary epistemologist, Jørgen Kvanvig, who says in one of his books that when we say that there is scientific knowledge, we mean knowledge only by courtesy. Strictly speaking, by the epistemologist standards, science has no knowledge. This is a peculiar statement in the ears of most philosophers of science. They would think that some of our best examples of what knowledge is from the sciences. So if an epistemologist says, to call scientific knowledge knowledge, it's only by vague analogy with real knowledge like here's a hand, or I know I'm currently in Edinburgh, then this is a very peculiar statement and is an expression of the distance between epistemology and philosophy of science. But it is my distinct impression that this gap between these two fields is becoming smaller, that there's more interest on both sides in the work of the other side. Specifically for the topic of relativism, I think this will be a good thing, because within epistemology, a number of approaches, new ideas have emerged on how to think about relativism, how to best formulate it, how to formulate the arguments for and against it more rigorously, and so on. Epistemologists have also become more interested in comparing relativism with respect to knowledge with other forms of relativism, in particular relativism in the domain of morality, where perhaps the philosophical sophistication with respect to relativism has been the greatest. So new ways of thinking, new models on how to think about relativism begin to move from these fields into the philosophy of science. That's one important development. Another important development is that philosophy of science has opened up more itself to politics and political questions. For example, thinking about science policy for a long time was not done by philosophers, but was done primarily by sociologists. Sociologists like Brian Wynne or political scientists like Sheila Jasanoff or Cass Sunstein were the people who thought long and hard about science policy. What kind of decision procedures do we want for deciding what kind of science do we get? Incidentally, footnote, Feyerabend was extremely interested in those kind of questions, but they were largely ignored because he was voicing those concerns at a time when philosophers of science weren't quite ready yet for this kind of opening. But that is happening before our eyes today. Philosophy of science and political philosophy have moved considerably closer. And it's no longer weird to have whole conferences or whole sections of international conferences devoted to the political philosophy of science. This has also meant that questions about relativism have received a new urgency and a new interest, because now political questions, the differences between societies and how do we adjudicate between different value systems, or how do we treat them in a tolerant or maybe even relativistic fashion, a reflection on those kinds of issues has become much more prevalent than it used to be. So the hope I have is that this exchange between philosophy of science and those other domains of philosophy will give us a better understanding of how to formulate maybe different forms of relativism, a variety of forms of relativism that might have a place in the study of science, and maybe also find new ways of adjudicating between them.
Hello, my name is Dr. Mark Harris. I'm a physicist who has become fascinated with foundational debates about science and the nature of reality. And in my work, I've learned a great deal from the history and philosophy of science and from theology. With this multidisciplinary hat on, I'll give you my perspective on the debate between creationism and evolution, while Dr. David de Pomeray, an evolutionary biologist, will later on examine the science. Now, when speaking of creationism, it's important not to be too sweeping. There's a wide variety of creationist beliefs, and it might be more accurate to speak of creationisms, as Ronald Numbers demonstrates in his magisterial history of the movement, simply called The Creationists. Well, one thing can be said for certain. Creationism is a religious position held by many Christians and Muslims worldwide, and I'll focus here on the most distinctive kind of creationism, Christian young earth creationism, which tends to reject biological evolution wholesale and to maintain that the Earth is only a matter of several thousands of years old, perhaps 6,000. And notable organisations which promote this kind of creationism maintain a high public profile. So Answers in Genesis, the Institute for Creation Research, or the Creation Research Society. All of these cater for many millions of adherents in the USA and worldwide. At first sight, the debate between creationism and evolutionary biology tugs at the heart of what it means to do science. Both sides proclaim that they're scientific, with creation science, scientific creationism, and flood geology being prominent examples on the creationist side. Also, both sides accuse the other of being unscientific, or in other words, of being a pseudoscience at best. There is a strong argument, though, for saying that this isn't principally a debate about how science should be done, but about where we derive our philosophical and or theological authority from to make claims about the world. Now, while mainstream evolutionary biologists are committed to the resolutely scientific process of observation, hypothesizing, and testing strictly within the confines of the natural world, young Earth creationism introduces a transcendent source of truth, the Bible, which trumps all others. The former group, like all natural scientists, derive their authority from the epistemological assumption known as methodological naturalism. But young Earth creationism further insists upon two supernaturally caused events, that they are creation and the flood, that change the whole picture. And the upshot for young Earth creationism is that the revelation of Christian scripture takes precedence over all empirical research on the origin and development of life, along with the age of the earth. And if that research isn't consistent with a literalistic reading of scripture, then the research is either modified until it is, or rejected outright. There's a sense, then, that the endless controversies between creation and evolution over the interpretation of empirical evidence largely miss the point, because the issues at stake are actually metaphysical, not scientific. Well, in the next video, I'll go on to explain the state of play here by charting the historical evolution of young Earth creationism and its strategies, before Dr. de Pommereny provides an overview of evolutionary science for comparison. One of the supreme ironies of the creation-evolution debate is that young Earth creationism is a relatively recent phenomenon, only gaining widespread momentum in the 20th century. Young Earth creationism draws inspiration for its biblical literalism not from long-standing Christian tradition, but from a key phase in the history of science. And two linked developments in the 17th century are important here. First, by combining the Protestant Reformation's insistence upon the comprehensive transparency of the Bible with the newly emerging empiricism of the natural sciences, a number of thinkers began to treat biblical text at face value as a source of data about the natural world, much like data from other non-scriptural sources. Second, the age of the earth and an account of its physical history became of special interest in this question. And the most celebrated attempt to date the earth was that of Archbishop James Ussher, who in 1648 made use of biblical genealogies such as Genesis chapter 5, along with ancient Near Eastern texts and astronomical results, to calculate that creation had occurred on Sunday evening, 23rd of October 4004 BCE, and the flood on Sunday the 7th of December 2349 BCE. In the same way, early accounts of the physical history of the earth took the biblical stories of creation and flood as providing reliable descriptions of what must have happened. Thomas Burnet's Sacred Theory of the Earth, published 1684, is notable for treating the biblical flood story in Genesis 6-9 not in terms of divine action, but in naturalistic terms. In this way, Burnet explained the form which the earth has today, including the shape of its continents. And not only did Burnet set a trend in geological thinking for much of the next century, which saw the biblical flood as decisive in shaping the earth we see now, well, his model is also essentially identical to that of contemporary young Earth creationism, as put forward in the seminal young Earth creationism text, The Genesis Flood, which was authored by John Whitcomb and Henry Morris, published in 1961. Well, going back to Burnett's model, the pre-flood Earth was totally smooth, but contained great underground cavities of water. These are the fountains of the great deep mentioned in Genesis 7, verse 11. And the flood was caused by these cavities being broken up. When the waters had subsided afterwards, the present shape of the seas and continents was left. While this model flies completely in the face of mainstream geology today, thanks to those 1960 authors, Whitcomb and Morris, it's adhered to by millions of creationists worldwide. Well, in between the 17th and 20th centuries, the scientific understanding of the Earth and its life forms advanced at a whirlwind pace. By the mid-19th century, developments in geology, paleontology and biology were indicating that the Earth was very old indeed, and that life had evolved over millions of years. These developments weren't especially troubling, however, for many conservative Christians who had found ways of harmonizing the new science with the Bible. So when faced with a biblical text like Genesis 1, which appears to insist that the physical universe was created in 6 days, many of these 19th century Christians took refuge in what's called the day-age theory, where each Genesis day was read as a figurative period, a much longer scientific period, perhaps millions of years. Or else they used the gap theory, where an immense time gap was understood to have occurred between God's creation of the universe in Genesis 1:1, that's the phrase "in the beginning," when God made the heavens and the earth, and then the 6 days described from verse 3 onwards. Well, these old earth creationist strategies, however, fell out of favour with many 20th century Americans who, when faced with new social pressures around what should be taught in high schools, preferred to adopt the most radical alternative to the mainstream scientific picture that we now call young earth creationism. The infamous Scopes trial of 1925 was a watershed here. The school teacher, John Scopes, was prosecuted by the state of Tennessee for teaching evolution in defiance of a state law prohibiting it. Well, the trial became something of a showcase for the creation-evolution debate, with the culpability of Scopes himself of less importance than the question of whether the Bible or modern science should take precedence in teaching about origins. The court proceedings were wide-ranging, concerning not so much the interpretation of the science, but the authority and interpretation of Scripture, and the wider impact upon ethical and political questions. In the event, the court found Scopes guilty, which had the effect of legitimating anti-evolutionary teaching for some time. This was by no means the end of the matter, though, and the debate started so publicly by the Scopes trial has ever since pitched two opposing worldviews against each other, with fundamentalist Christianity on the one side and modernity as represented by evolutionary science on the other. So the context of the Scopes trial and the emergence of young earth creationism was clearly a social and historical phenomenon of the early 20th century, namely the growth of fundamentalist Christianity in American society, led by figures such as William Jennings Bryan, who was one of the main players in the trial. This movement was attempting to establish its conservative brand of Christianity as an intellectual position in its own right, against what were seen to be liberalizing tendencies based on scientific naturalism, especially German biblical criticism and Darwinism. The fundamentalist argument was that these tendencies were examples of a false science, which steadfastly refused to countenance miracles and supernaturalism. True science, on the other hand, would be open-minded about such things, and crucially, would support a literal interpretation of the Genesis creation stories. But this fundamentalist kind of true science wasn't to reach its definitive formulation until 1961, when Whitcomb and Morris published their famous book I mentioned earlier, The Genesis Flood. This ensured that young earth creationism would thereafter be a statement about the significance of Noah's flood, as much as it was a statement about the age of the earth and the failings of evolutionary science. It's no exaggeration to say that this single book has done more to influence the shape of young Earth creationism as we know it now than any other. Effectively, they repackaged the earlier ideas of the Seventh-day Adventist writer George Macready Price, along with the far earlier ideas of Ussher and Burnett, but with barely a nod to either of them, and this book made the case that the biblical flood provided a catastrophic and divinely caused alternative to the naturalistic paradigms provided by mainstream geology and paleontology. As with the earlier fundamentalists of the early 20th century, Whitcomb and Morris saw this as a matter of true science, their own, against the false science of mainstream, especially evolutionary biology, and for similar reasons as those earlier 20th century fundamentalists. The Bible must be held as completely trustworthy, maintained Whitcomb and Morris, in describing the two divinely caused events of creation and flood. The biblical flood is a witness and a warning, they believe, and to doubt this is to doubt God's power to save human souls. In this way, true science must begin with the revelation of Scripture and must not moderate it through human philosophies, such as evolution. Therefore, human beings, like all other life, were created by God in the literal 6 days of the initial creation, before the flood swept them away, apart from what was preserved on the ark. This much was a literal reassertion of the biblical text, like the earlier fundamentalists. But unlike those earlier fundamentalists, Whitcomb and Morris in 1961 engaged extensively with the geology and paleontology of their day. Hence, much of their book, The Genesis Flood, gives a reinterpretation of geological evidence in order to support their view that the flood was a universal cataclysm and that the Earth is very young. It's not my purpose to assess Whitcomb and Morris's arguments in detail here. Many others have done this to great effect, illustrating that Whitcomb and Morris treat the relevant science in a highly selective way, the better for them to twist it into their version of Burnett's 17th century model of the Earth. And such is the force of their rhetoric that it comes over as highly plausible to those Christians who have a little knowledge of mainstream geology and evolutionary biology. But what I do want to highlight, however, is the calls which creationists such as Whitcomb and Morris make on the philosophy of science. And key here is Francis Bacon's idea that science is principally inductive, that science makes generalized inferences from many direct observations. So citing Bacon's work of the 17th century, creationists frequently claim that historical sciences such as paleontology and evolutionary biology cannot be scientific because they can't make direct observations of what actually happened in the past. Instead, the best that such subjects can do is to make untestable and hypothetical speculations, goes the argument. Now, it's interesting to note that Darwin himself faced this accusation over Origin of Species. But the fact that Darwin and his successors weren't deterred, but slowly built up the enormous edifice of evolutionary science we know today, indicates two things, I think. First, that empirical science is more sophisticated than Baconian induction might suggest, and second, that if the creationists' true science is strictly Baconian, then it can only bear a passing resemblance to the natural sciences of today. In short, there are good reasons for judging young Earth creationism to be stuck in a pre-19th century view of science, both in method and in content. In order to take this point further, Dr. de Pommeray later presents a brief overview of evolutionary biology as it currently stands.
Evolution and Creationism. David de Pommeray, New College, University of Edinburgh. The concept of evolution. Nothing in biology makes sense except in the light of evolution, as Theodosius Dobzhansky remarked in 1973. Evolution is the underlying process that gave rise to the prodigious variety of living organisms on Earth, otherwise biodiversity, including ourselves. It has generated countless new species during the history of life, of which 99% are now extinct. Each species is adapted to its local environment or ecological niche, but changes in climate, geography, or biotic factors such as other organisms alter that environment over varying timescales, causing extinction or providing opportunities to diversify into new, better adapted species, termed speciation. 5 mass extinction events have punctuated Earth's history, the most recent wiping out dinosaurs about 66 million years ago. There is little doubt that a 6th such event has been set in motion by anthropogenic climate change. Current evolutionary ideas stem principally from Charles Darwin's Origin of Species in 1859. Evolution can be summarized as descent with modification, but this phrase requires unpicking. Animals or plants normally give rise to similar offspring despite minor variations. The so-called neo-Darwinian synthesis combines Darwin's insights with those of genetics, stemming from Mendel's work on the inheritance of traits. Descent in multicellular organisms usually involves 2 sets of genetic information, DNA, derived from the father and the mother. This diploid genome consists of long sequences of DNA termed chromosomes, which include the genes, each specifying 1 or more proteins that contribute to the characteristics of the offspring. Variant versions of the same gene, known as alleles, often differ in function to a greater or lesser extent. However, protein-coding genes comprise only a small fraction of the total DNA genome, and much of the rest has regulatory functions that are not yet fully understood. Some genes are duplicated, and extra copies may become redundant pseudogenes or specialize for new functions. Darwin envisaged a tree of life whose branches ramify into new species twigs. The fact that all living things use DNA as their genetic material, with similar mechanisms for translating that information via RNA into proteins, implies that they have all diversified from a common ancestor. Importantly, however, the genes transmitted to offspring are not invariant. Beyond the scrambling of parental genes that occurs during gamete development, sperm or eggs, pollen or ova, there are also random changes in the DNA sequence resulting from genetic mutation caused by radiation or by chemical damage. Usually such damage is accurately restored by DNA repair systems to the original sequence, but sometimes this fails, resulting in a point mutation. Such changes can occur within a gene or in the neighbouring regulatory regions, though sometimes larger genetic changes arise. DNA sequence changes within a protein coding gene commonly cause alterations in the encoded protein. Again, the effects vary considerably, ranging from deleterious effects on function, as in human genetic diseases like sickle cell anemia, through marginal or neutral effects to functional improvements, enabling that individual to reproduce more successfully in a changing environment or a different ecological niche. Such beneficial mutations are admittedly rare, but can spread rapidly within a population, provided there is sufficient selection pressure. If space and food are abundant, populations of organisms will expand geometrically, as first noted by Thomas Malthus. When resources become limiting, this is no longer possible. Darwin's key driver for evolution is natural selection. Essentially, a given set of environmental conditions, biotic factors such as food supply, predation, or disease, promotes the reproductive success of individuals carrying certain favourable mutations. but also selects against other less favourable mutations. Selection can be applied artificially by humans, as in selective breeding of crop plants, for instance the many vegetables derived from wild cabbage. Also livestock animals or pets, generating the huge variety of modern breeds within the short timescale of human history. Inadvertent artificial selection is also well documented, notably the ability of pests to evolve pesticide resistance, often within a few years. The distinction between favourable and unfavourable mutations is context dependent rather than absolute. The sickle cell mutation is common in West African populations, even though full-blown sickle cell disease in individuals with 2 mutated gene copies is usually fatal. However, carriers of the sickle cell trait with 1 normal and 1 mutated gene copy are not only healthy, but also have increased resistance to malaria. The combined effects of all genes on an individual's reproductive success, as reflected in progeny numbers, is described by the aggregate term fitness, and this is what is implied by survival of the fittest. Artificial selection, as in the examples given earlier, has produced significant changes within very short timescales compared to the 4.5 billion year age of the Earth and 3.5 billion years of life on its surface. These timings are in turn based on the geological record, using best estimates for the ages of different rock strata derived from invariant rates of isotope decay. It is plausible that geological time spans are sufficient to allow the diversification of life on Earth through evolution by natural selection. The taxonomic system used today originated with the Swedish naturalist Carl Linnaeus, who employed morphological criteria to classify animals and plants in his book Systema Naturae, the 10th edition dating from 1758. Each distinct type of organism is given a Latin binomial classification, the first name denoting the genus or group and the second the species. The genus Homo includes only 1 extant member, Homo sapiens, plus extinct species such as Homo erectus, H. neanderthalensis, and H. floresiensis. Genera are grouped into families, such as the orchids, Orchidaceae, and families into orders, such as beetles, Coleoptera, or bees, etc., Hymenoptera, or butterflies and moths, Lepidoptera. Orders are further grouped together into classes, Hexapoda in this case, and these in turn into phyla, sharing a common body plan. The phylum Arthropoda includes insects, chelicerates, spiders, etc., crustaceans, and myriapods. Low-cost rapid DNA sequencing provides independent insights into the underlying genetic relationships between organisms. This largely confirms an evolutionary basis for Linnaean classification, but there are cases of deep genetic differences between similar-looking organisms and unexpectedly close links between dissimilar species. Since DNA mutation occurs at a fairly constant rate, one can infer the timing of branch points when species diverged by building phylogenetic trees based on DNA sequence data. New species often arise through reproductive isolation, e.g. when organisms colonize an island. In the Canary Islands, for example, certain plant genera contain numerous species that are far more diverse than their mainland relatives. Examples include buglosses, Echium, or spurges, Euphorbia. This results from adaptive radiation, where the progeny of founder individuals adapt to a whole variety of available ecological niches. Several Canary and Euphorbia species have evolved into cactus-like forms adapted to drought. even though true cacti belong to an unrelated family. Both arose by convergent evolution, whereby similar adaptations, an optimal design solution, have arisen independently in different groups that do not share a common ancestor with the same trait. Box camera eyes in vertebrates and in cephalopods, as well as in other animals, provide further examples of convergence. Related species are usually unable to interbreed, though in some families, like orchids, hybridization is common, suggesting that reproductive barriers are not inevitable during speciation. Given a stable ecology, well-adapted species can persist for millions of years without appreciable change. Witness living fossils, such as deep-sea coelacanths, which differ little from their ancestors 400 million years ago. However, the fossil record from sedimentary rocks is patchy and incomplete, with soft-bodied organisms poorly represented. Even for species whose hard parts are readily preserved, such as mollusk shells or vertebrate bones, there are gaps and anomalies in the fossil sequence, though occasionally a near-complete series of intermediates links early with modern forms, for instance with elephants. These exemplify gradualism, denoting slow progressive evolution over time. In apparent contrast to this stands Stephen Jay Gould's theory of punctuated equilibria, which postulates long periods of stasis punctuated by periods of very rapid evolutionary change. This is in part an optical illusion. Beyond the acknowledged incompleteness of the fossil record, periods of rapid evolution often follow mass extinction events, when surviving species diversify to fill environmental niches occupied previously by now extinct organisms. Long periods of gradual evolutionary change are therefore punctuated by bursts of adaptive radiation that are brief, geologically speaking, but still span millions of years. Many genes operate in tightly controlled networks, such that mutations in a regulatory upstream gene can have multiple pleiotropic effects on the downstream genes whose expression it controls. This is particularly true of the so-called master genes that direct animal and plant development, such as the homeotic Hox genes governing regional identity in many animals, or heterochromic genes specifying developmental timing. Mutations affecting the regulation of these genes can lead to changes in body plan or life history, potentially contributing to rapid evolutionary change. The origin of life. Descent by modification implies a common ancestor, an organism that must have emerged during the first billion years of Earth's existence. Presumably, this organism already used DNA as its genetic material, and probably resembled the archaea that survive today in extreme environments, such as hydrothermal vents and hot springs, deriving their energy from exotic chemical reactions. Inferred conditions on the young Earth's surface were probably conducive to the spontaneous formation of organic molecules, providing vital building blocks for life. However, it is a huge leap from puddles of primeval soup containing the requisite ingredients to a living cell capable of reproducing itself and passing on its DNA. Perhaps the first life forms were based on RNA, which can act both as genetic material, for instance the RNA genome in retroviruses, but can also carry out many protein-like catalytic functions, termed ribozymes. But RNA-based life forms have left no descendants today, and other possibilities remain open. Recent discoveries of planets orbiting other stars raise the possibility of life evolving elsewhere in the universe. But it is also arguable that ours is a rare type of planet, unusually favourable for evolution of life based on the unique chemical properties of carbon in a watery environment. For much of Earth's history, life was microbial, leaving fossilised mats and three-dimensional stromatolites generated by unicellular bacteria or prokaryotes. Higher organisms, like fungi, plants or animals, are mostly multicellular, allowing different cells to specialise for particular functions, differentiation. For instance, animal nerves or muscles. This became possible thanks to the emergence of novel eukaryotic cells, which are essentially combinations of two or more prokaryotic cells, one living symbiotically within another, the endosymbiont hypothesis of Lynn Margulis. At least two intracellular organisms within plant cells originated in this way, the energy-producing mitochondria and the photosynthetic chloroplasts, each derived from a different prokaryotic ancestor. Animal cells have mitochondria only, but efficient energy production using oxygen is essential for their active lifestyles. Thus, evolution can involve elements of cooperation and networking. It is not all red in tooth and claw. During the Ediacaran era, 630 to 540 million years ago, the oceans were inhabited by strange organisms that lack any obvious affinities with familiar animals or plants. Within a relatively brief period, termed the Cambrian explosion, starting about 540 million years ago, these biota virtually disappeared and were replaced by animals belonging to modern phyla, including arthropods, sponges, comb jellies, marine worms, and chordates. These assignments are supported by exceptionally well-preserved Cambrian fossils, including traces of soft body parts. However, many of these fossils remain enigmatic, to say the least, because their body plans seem unlike those of modern animal groups. For Stephen Jay Gould, these anomalies represent novel body plans that did not survive the ravages of natural selection and hence became extinct. Provocatively, he claims that if the tape of evolution were rerun from the Cambrian, we might find ourselves today in a world dominated by a very different selection of organisms. Gould emphasises the randomness of survival in the evolutionary lottery, scotching any notion of progress from lower to higher forms, culminating in humans. However, Simon Conway Morris interprets these fossils very differently, as intermediates or ancestors in the appearance of new animal groups. He focuses particularly on convergent evolution, adducing numerous examples of this process and arguing that only certain design solutions actually work to enhance fitness. Hence, these adaptations recur repeatedly in independent lineages. The example of box camera eyes was cited earlier. Likewise, the convergent adaptations against drought adopted by cacti and by some euphorbias. Extrapolating speculatively from this, intelligent bipedal life may be a predictable outcome from prolonged evolution in a benign planetary environment. One suggested compromise between these positions is that these now extinct Cambrian animals belonged to major class-level groups, as distinct from modern groups as insects are from crustaceans, but did not represent completely different body plans corresponding to vanished phyla. Other later class or order level extinctions include the arthropod trilobites, molluscan ammonites, and reptilian dinosaurs. Evolution moulds not only physical attributes, but also patterns of animal behaviour. Because fitness is measured by success in transmitting genes to offspring, reproductive traits have been subjected to intense sexual selection in one or both sexes, affecting structures and behaviours involved in courtship and mating. The elaborate tail feathers of male peacocks afford one obvious example, as do the heavy antlers of many male deer. Since these exaggerated physical or behavioural attributes are interpreted as indicators of a sexual partner's fitness, these can become runaway evolutionary trends. Plant pollination by specific insects also creates selection pressures for one or both species, leading, for instance, to deeper flowers and longer mouthparts, a trend which can be carried to astonishing extremes. The 25-centimetre long spur of the Madagascan comet orchid requires a hawk moth pollinator whose similarly long proboscis allows it to feed on nectar at the base of the spur. There is, however, a cost. This plant cannot be fertilised by any other insect and is entirely dependent on the hawk moth. The two have co-evolved, so if the moth became extinct, the orchid would be doomed. Innumerable other examples of mutual dependency between organisms are known. Often, though not always, there is clear benefit to both in such associations. In parasitism, the benefits seem entirely one-sided. Parasites gain nutrients and a sheltered environment, though host immune responses attempt to combat the invader, while hosts suffer mild to debilitating disease. Parasite levels affect host behavioural patterns, such as dominance hierarchies and reproductive success. Here, an arms race is in progress. As the host evolves new immune strategies to control the parasite, natural selection encourages the latter to evolve better ways of countering or invading them. The end result is often a parasite species uniquely adapted to a particular host and its specialized immune system. Humans share over 98% of their DNA with chimpanzees, and rather less with other great apes. Patterns of animal behaviour are often instinctive rather than learned, suggesting they are hardwired in the nervous system by that animal's genes. That said, most behaviours can be modified by learning through experience. Other behaviours can be learned from conspecifics, such as parents or group members, resulting in cultural variance particular to local groupings. But humans take this to extremes. Diverse cultures have evolved rapidly over time, as documented in both written and archaeological records. Richard Dawkins has proposed a second form of evolution in human societies, in which the fundamental replicators, analogous to genes, are units of culture termed memes, subject to Darwinian natural selection just like genes, but over far shorter timescales. Memes, like genes, are difficult to pin down, and this concept has both enthusiastic supporters and fierce critics. Even so, humans clearly do pass on ideas, concepts, and artistic works to others, both contemporaries and future generations.
We're now in a position to answer the question in the title of the module, Creationism and Evolutionary Biology, Science or Pseudoscience. The precise definition of science is notoriously difficult to pin down, but Dr. de Pomerei's overview has hopefully demonstrated that evolutionary science qualifies on many counts not least for its amazing explanatory scope across a huge range of biological questions, for its incorporation of many diverse kinds of scientific inquiry within itself, including branches of physics and chemistry, which no one disputes as science, and for its ability to spawn fertile new research programs. The accusation of young Earth creationism, that evolutionary theory isn't scientific, seems churlish, to put it mildly, in light of this phenomenal success. In any case, if we were to exclude evolutionary biology from the natural sciences on account of the grounds that it's insufficiently Baconian, then we'd need to look closely at other branches of the modern natural sciences too. For sure, it's true that so much of evolutionary history isn't accessible by means of direct experimentation in the laboratory, but this doesn't provide a basic empiricism in historical sciences like evolutionary biology, geology, and astronomy. They proceed just like the other natural sciences by means of a cyclical process of observation, hypothesizing, searching for more evidence, and revision or rejection of the initial hypothesis. In comparison, young Earth creationism fails dismally as an empirical science. Indeed, there's a strong case for suggesting that young Earth creationism doesn't even qualify as a pseudoscience on this score. Young Earth creationism makes claims or hypotheses that are open to empirical testing, principally the young age of the Earth and the worldwide extent and cataclysmic character of Noah's flood. But these have been shown to be entirely false by the mainstream empirical sciences countless times. And yet, young Earth creationism persists in making these claims. In other words, young Earth creationism is such a failure as a science, and even as a pseudoscience, I would say, that it can't reasonably be claimed to be one. Young Earth creationism takes its certainty not from any body of knowledge about the natural world, but from a transcendent source, the Bible, upon which it will not budge a single inch. It's therefore my contention that evolutionary biology is certainly scientific, but that creationism in the form of young Earth creationism is neither scientific nor pseudoscientific, it's theological. If the natural sciences are committed to an epistemological naturalism, then young Earth creationism is committed to an epistemological supernaturalism, and there's really no reason we should confuse the two. Let me summarize. There are various creationisms, but young Earth creationism in particular has persistently challenged the scientific claims and status of evolutionary biology. Young Earth creationism arose in the 20th century, arguably as a conservative religious backlash against progressive modernism. Young Earth creationism offers its own distinctive science, which posits a young Earth and a worldwide flood which shaped the Earth's present geology and fossil record mere thousands of years ago. Both sides of the creation-evolution debate accuse the other of not being scientific, although their definitions of science seem to be widely divergent. While the claims of evolutionary biology are based on painstaking observation and experimentation of the natural world by thousands of individuals working across a wide spectrum of life sciences, those of young Earth creationism must conform above all to a literalistic reading of the Bible as the primary source of evidence concerning origins. One particular bone of contention concerns the question of whether study of the past can be truly scientific, since it can't be observed in the laboratory. Young Earth creationism argues that the evolutionary history of life is an unscientific hypothesis which rejects the preeminent status of the Bible as a source of both scientific and religious truth. But mainstream evolutionary science is committed to methodological naturalism and doesn't rely on transcendent sources of truth. Instead, sophisticated methods of study have been developed to investigate the history of life in empirical terms. The starting assumptions of evolutionary biology are quite different to young Earth creationism, and while the formers fall squarely within those of mainstream science, young Earth creationism represents a totally different worldview, which can't be described as scientific in any conventional sense.